where data, automation, and artificial intelligence inspire new forms of innovation and opportunities we can only imagine. Advancements in 5G communications, autonomous driving, cloud, and hyperscale computing are delivering a deluge of data, offering compute challenges for those most able to adapt. Strategic thinkers are embracing tomorrow's challenges today. The visionaries, the disruptors, the architects of possibility. They see that integration and intelligence will be designed into the products of the future. They know the industry demand for holistic system design, for mobility, hyperconnectivity, performance, and reliability. The path forward will not be easy. You will need a trusted partner who can help get you there. Someone with the breadth and depth of technology to anticipate what's ahead. A company with the right combination of tools and expertise to empower you to create the products of the future. Go on. Unleash your imagination.
Technology. It makes us think of numbers, data, analytics, and math. All the stuff that goes on in our head. But the truth is, the head is powerless when it's not fueled by the heart. And memory is the heart of technology, the driving force that pumps life into every product, application, and innovation it touches. Memory is the heart of science, allowing researchers to explore the microscopic detail of the human body and the infinite grandness of the universe. Memory is the heart of industry, making precision agriculture more productive, vehicles more autonomous, and smart homes more convenient. It is the heart of consumer experiences, making esports more active and VR more interactive. And it is the heart of AI, enabling it to do everything from make us coffee to make us laugh. At Micron, accelerating intelligence is more than a science. It's a passion, which is why we've assembled more than 37,000 thinkers and doers in over 18 countries who know that innovative memory solutions are essential to our future. A promise to continue pushing the limits, shaping the way we live, the way we work, the way we see the world. Memory is at the heart of what makes the impossible possible. And we are the memory makers. Micron, intelligence accelerated.
Dr. Prasanna Muhim and David McCarthy. We welcome you all to give this first tutorial on the second day of the VLSI Design Conference. Would we be able to start the video, please? Oh, they requested 1 minute. Just give us 1 minute. So until then, I will just mention I'll just introduce Professor Forrest Brewer. Forrest Brewer has 32 years experience as a professor and has published over 100 technical papers in the general area of VLSI. He has actively worked in pulse gates since 2004 and been involved in the design of pulse gate-enabled designs from 0.6 micrometers to 22 nanometer FTSOI nodes, including 130 nanometer radiation-hardened designs for CERN LHC LMS. And Prasanna Muhim, I hope I am pronouncing it correctly, received a PhD in electrical and computer engineering from the University of California at Santa Barbara in December 2020. Her research was on the analysis design of precision timing circuits using pulse mode signaling. She's currently working as a postdoctoral associate at the University of Maryland and National Institute of Standards and Technology, Gaithersburg. And David McCarthy is a PhD candidate in ECE at the University of California at Santa Barbara. His research is on electronic design automation for asynchronous circuits. Before that, he received his BE and MNJC from University College Cork in Ireland in 2013 and 2014, respectively. I think we are ready to go. So I think when the hosts are ready, please go ahead and play the video. Thank you.
Welcome to the VLSI 2021 High Performance IP Design Using Pulse Logic tutorial. I'm Forrest Brewer. This is work also presented by Prasanna Muhim and David McCarthy. Contributions by Merritt Miller, Aditya Dalakoti, and Kerry Siegel. Introduction. This work, at least for us, was sponsored by, in part, by radiation work, link work we were doing for CERN. And in particular, we've been looking into doing data distribution from compact muon selenide, which I have to point out isn't really so compact. It's 30 meters long and 10 meters tall apparatus along the beam line of the Large Hadron Collider. And the problem they had was that they were spending something to the tune of 150,000 watts, 130,000 watts, getting data out of this experiment, petabytes of data, from literally something on the tune of 4.5 million sensors. And as the device was being rebuilt, the be 3 or 4 inches or 5 inches away from each other on a PC board. And the question was, could we make a low power link that would be IP for various sensor components and then would integrate into a data concentrator that could get data into fiber or other formats that move it out. The problem, of ions would fly through your chip, which would cause massive SEU issues that you'd have to recover from. In that light, the question of whether we could use PLLs or DLLs, what's the recovery time going to be? And the idea as well that you had something like maybe 25 to maybe 100,000 of these links in the system. if recovery time was tens of microseconds, how much data would you lose? And how many of those links could simultaneously be active when the system was actually operating? Then there were questions about long-term drift and power noise. And those issues all kind of scared us, to be honest, about trying to do things in conventional 130 nanometer design. So instead, we built a design using pulse logic, and roughly, you can see these are actually sort of cadence micrographs, if you like, of the pad ring. This is a differential pad driver on the output, and you can see these B is the protection diodes for that logic. These are 70 micron wide pads. The C guys here are, in this case, two basically 12-way parallel drivers. They were built that way, decoded locally, to essentially create a lot of redundancy in the drive, because if one of these guys gets hit by a particle, the rest of them, by just averaging, will give rise to a proper output. But the interesting thing is that the entire link was actually this part D up here. This thing on the backside is basically decoupling diodes, but this is actually the entire IP, which is something like 60 microns by maybe 110 microns in footprint. And the thing is, that's triply redundant. So there are literally 3 full copies of everything going on in there to make sure that the construction would work, even in the presence of pretty massive SEU information. The receiver is much the same. I've got drivers coming in, protection diodes. Here I've got basically 2 clusters of 3 parallel copies of amplifiers. And so if one of them goes out, you're looking at the data from all 3 of them. And then triply redundant decoding. So this is basically an 8-bit input, 8-bit output link, moving data at something like, in this case, 5.1 gigabits a second, transmit and receive, fully asynchronous. Side effect of doing the design this way was that the idle power was next to 0. I mean, really was very, very, very low. They had quite tiny layout footprint. You can see there's no PLL here, no DLL. We're still getting 5.1. This is actually measured numbers. The hardness was way beyond. In fact, we tested it to 350 megarad and had almost no deviations. We were actually running some of this actively during that test. Disruption restart was less than 3 nanoseconds, which meant that we didn't have to worry about resynchronization. It was fire and forget. That was all good. The downside, of course, it was completely incompatible with conventional test equipment that was being built for this technology. And so CERN, being the sensible people that they are, decided indeed that although this was really interesting, and in fact they used some of the numbers to drive down their own power requirements for their own links, chose instead to use conventionally testable things, which in a lot of sense does make sense. The expected behavior was what we got here. This is actually an oscillogram of the actual link, and you can see the 2 different channels basically interleaving properly, bits going out at an appropriate scale. When we started doing these measurements, we thought, gosh, those oscillograms look a lot better than we expected for a link that was operating what essentially is fully asynchronously. In particular, we knew we had about a 10 megahertz per millivolt rate sensitivity, and we were doing this with a power supply that we knew had 30 millivolts of power noise. The oddball thing is that normally you'd expect that at some point around time 0 where you're syncing, you get these nice pulses, but if you start walking away, things get blurry, right? And the reason is that jitter builds up, and pretty soon in an asynchronous design, there's nothing to bring it back into lock with your system. So, you just lose the eye and it gets to be something that you can't see. The odd thing is that this self-timed circuit, which is the entire link design running PRBS data, was actually coherent out beyond 200 cycles with, this kind of variance in its power voltage. And that made no sense at all to us. And so we then turned around and ran histogram pulse arrival times and got this. And you can see that the spacing of these pulses is slightly different. Slightly not even, because of course there's round the loop deviations in the actual circuit design, because the circuit was actually literally laid out as a set of standard cells and wires. But oddly enough, we were getting jitter that was on the scale of 1.5 picoseconds. And we'd have been proud if we'd made a conventional link, we had a jitter figure that was on that scale. This is measured jitter of the output pulses. And we never designed it to do anything like that. And indeed, with this kind of rate sensitivity, we expected we couldn't understand how this was actually happening. And the question was, what caused this anomalous stability? So we ended up with doing pulse design. The footprint was small. The jitter was surprisingly small. The logic family is self-timed, which meant that it's pretty easy to build. Custom layout performance we got was from standard cells because we didn't have much time to do that. But nonetheless, we were getting performance levels that were pretty close to what people were doing in full custom designs, full custom IP. Suited for timing, synchronization, arbitration protocol circuits. We can see that easily. The clock timing parts of ADCs and sampling front ends and complex all seemed like there'd be something we could use this kind of design. And the reason is because the timing closure is fundamentally different than the classical way of doing things in standard CMOS. So in this tutorial, we're going to talk about the properties of pulse gates, a little bit about pulse buffer design, pulse mode signaling, building logic functions in those designs, layout technology, electrical properties, a couple of examples of different pulse link applications, including multi-phase pulse clocks where the collective behavior of pulses becomes exploited, and timing verification strategies, which have come up recently, that you can actually validate that functionally the circuit that you built is the one that you wanted.
I'm Prashanta Mukim, and I'll be presenting the next few sections of this tutorial, which include the properties and performance of pulse gates, as well as the design of a few high-performance IP using pulse gates. So the basic building block of pulse logic is a pulse buffer, which accepts a pulse input and produces a buffered output pulse. And its working is shown on this timing diagram, where on the arrival of the rising edge of the input pulse, the critical node of the pulse buffer is pulled down, which causes a rising edge to occur on the output node. And as the critical node is pulled down, the reset node is also pulled down, which activates this pull-up transistor and causes the critical node to be pulled high. And as the critical node is pulled high, a falling edge is produced on the output node. Thus, we have finished the process of creating a pulse on the output of this pulse buffer. And after the delay of 2 inverters, the reset node also ends up being at a high voltage potential, turning off the pull-up PMOS transistor. So in the steady state, both the reset node and the critical node are at a high voltage potential. And in the absence of pulses, the pull-down transistor is also turned off. So we use this keeper loop to restore charge on the critical node. And it should be noted here that the pulse width of the output pulse is primarily set by the delay of the reset loop. So pulse logic is a non-inverting rising edge sensitive logic family, which is similar to domino logic. But here these gates are self-resetting and there is no global clock that is distributed to every gate. And we can see that pulse logic contains more transistors than static CMOS gates. So it can be more expensive than static CMOS in terms of area and power. But in this tutorial, we will present examples that show how pulse logic enables the design of high performance timing and communication circuits, which lead to overall low system power. So pulse logic is a dual rail logic family, and it uses 2 wires to encode information. And in the example shown here, occurrence of a pulse on wire 1 indicates that we are transmitting a 1. Occurrence of a pulse on wire 0 indicates that we are transmitting a 0. And another thing to note here is that we are using pulses to encode both data and timing. We don't need a separate sampling clock. And the latency between pulses also doesn't matter. As long as the correct ordering of pulses is maintained, the circuit behavior will be correct. As far as detection of pulses is concerned, a pulse gate will trigger as long as the input pulse has sufficient amplitude or width to integrate a critical amount of charge at the critical node. This is what this equation here is showing. So both high amplitude but narrow pulses, as well as lower amplitude but wider pulses, will cause the gate to trigger. And in either case, the shape of the output pulse will largely depend on the delay of the reset loop and not the shape of the input pulse. So this also simplifies the process of shifting between different voltage domains. There are two alternative architectures for the design of driver and feedback networks of pulse gates. The first one shown here is a load isolated structure where an inverter is isolated from the feedback loop of the pulse gate, and that's the one which drives the load. So here the output load has no effect on the shape of the output pulse. In the second architecture shown here, this is essentially a load sensitive feedback system, and the output driver is a part of the feedback loop. So the load being driven does affect the pulse shape. It essentially broadens the pulse shape if a high load is being driven. But this structure is more robust when we are driving high capacitive loads. Here the I/O waveforms for both architectures are shown. So when the output load is relatively low, the timing of the two gates is similar. However, when the output load is high, the load sensitive feedback architecture produces pulses that are slower and wider, but these pulses also have a higher amplitude, which increases their likelihood of detection by the next stage. So for sizing pulse gates, we assume that the keeper transistors are smallest, as we are only using these to restore charge on the critical load and reject some amount of noise. Next, the pull-down transistors should be big enough to overcome the charge stored by the keeper node. And higher drives on the pull-down transistor also lead to sharper output rise times, thus reducing the jitter in the output pulse. So the pull-down transistors are sized at least 2 times to be bigger than the keeper loop transistors. The pull-up PMOS transistors are 4 to 6 times stronger than the keeper transistors, and a stronger drive on the pull-up transistors ensures that we do set the pulse width by the reset loop and not by the shape of the input pulse. And finally, the feedback loop inverters and the driver inverters, the sizing should be chosen based on the expected load that we plan to drive and on the desired pulse width. This plot shows the pulse width preservation property of pulse gates. So it shows the results of an experiment where a chain of pulse gates was simulated, and the width at the end of the pulse chain as a function of the input pulse width is plotted. We see that narrower pulses are elongated and wider pulses are trimmed. So in pulse gates, pulses converge to a uniform width when driven by a chain of pulses. Now, in order to implement different logic functions, we can change the pull-down network of pulse gates. Here we show 2 examples, a pulse OR gate that triggers an arrival of either input pulse, and a pulse AND gate that produces an output pulse on the arrival of the input pulse if the voltage on this lower NMOS is a logic high. Essentially, this gate implements guarded pulse generation, and we can make the pull-down network more complex. It can have multiple parallel stacks of transistors to implement more complicated logic functions. However, one important rule to keep in mind is that each stack should be designed to have a single pulse input. We avoid operations where we do AND operations between pulses. So this picture here shows the generic pull-down network of a pulse gate that has 1 pulse input in each stack and a combination of level inputs, and it produces an output pulse. We also make use of latches in this logic family to store state and convert pulses to levels. The latch shown here is an OR latch, where we implement logic inside the latch itself as opposed to using a separate gate. This is a summary of the composition rules for pulse logic. There are 2 distinct signal classes, data, which is communicated by high or low levels, and events or pulses, which are communicated using atomic pulses, and these are the signals which cause the system state to change. Then there are also 2 distinct gate classes, D gates or data gates, which are gates with memory, essentially latches, and the output type is a data or a level. And P gates or pulse gates, which are gates without memory, output type is an event. And these are the two most important construction rules to keep in mind when building pulse logic. The first one is that data must be stable in the setup or hold window relative to pulse arrival. So if a gate operates on a composition of level and pulse inputs, the level should be stably set before the arrival of the pulse, and it should not change at least for the duration of the pulse width. And the second rule is that gates can only have one active pulse at a time. So we avoid pulse ANDing and operations that rely on the overlap of pulses. Here we show an example where a 3-bit counter is constructed using pulse logic. The green arrows are all pulses and the blue arrows are all levels. Here bit 0, bit 1 and bit 2 are the 3 output bits of the counter. Count is a pulsed event on whose arrival the count is incremented, and reset is an asynchronous reset event for the counter. On arrival of the count event, the bit 0 guard is first evaluated, and the first SR latch is toggled based on the current value of bit 0. In addition, we have this gate C1, which produces an output event if bit 0 is a 1. And this happens on the occurrence of the count event. The output signal from C1 triggers the SR latch for the next bit, that is bit 1. And the signal produced by gate C1 also drives gate C2, where the guard on bit 1 is evaluated. And an event is produced for toggling the third latch corresponding to bit 2. So essentially here we have a chain of toggle latches. And finally, a done signal is produced when all bits have finished toggling in response to the count stimulus. And the occurrence of done indicates that now it is safe to sample the output bits of the counter. Here we show the circuit implementation of the 3-bit counter using SR latches and pulse AND gates, which evaluate guards and generate events for the latches. And we also use pulse OR gates to concatenate done signals from different parts of the circuit and produce a single done output. And these are the timing waveforms. On the arrival of the reset pulse, all the 3 bits of the counter are reset. And on every count pulse, the count is incremented. And once all the bits have toggled in response to a count pulse, a done pulse is generated. So far we have laid emphasis on the fact that pulse logic only allows a single active pulse input at any given point of time. But consensus and arbitration gates are 2 multi-pulse input gates, which are an exception to this rule. They allow multiple active input pulses and are used for synchronization between independently created smaller logic blocks. So for a consensus gate, each half of the consensus gate, or the 2 input consensus gate shown here, integrates and stores charge on the arrival of an input pulse. And the gate finally produces an output pulse when both input pulses have arrived, and then both halves are reset. Whereas an arbitration gate accepts 2 pulse inputs, and if these input pulses happen to be close to each other in time, the arbitration gate will produce output pulses which are spaced apart in time, as can be shown on the input-output timing diagram in this figure. The arbitration gate can be designed to arbitrate for relative separations as small as 1 picosecond. And once again, both of these gates are useful for synchronization at block interfaces. So here we are comparing how pulse signaling compares against edge signaling on on-chip wires. So we simulated a 5 millimeter long wire with 4 internal buffers. and we measured the propagation delay for a 100 picosecond rising edge and a 165 picosecond pulse, which have interwire couplings of various kinds. And we see that for all these different cases, the propagation delay of pulses is very similar to the propagation delay of edges. And we also see that the standard deviation of the propagation time is similar. And interestingly, pulses show a slightly smaller deviation in the propagation time compared to edges. And this is attributed to the self-resetting property of pulse gates, which protects pulse widths. And unlike static CMOS logic, where we see evaporation of pulses along wires, we don't see that when we buffer these pulses using pulse gates, because pulse gates are designed to protect pulse widths. So here we show how the weights of pulse gates compares against various of static CMOS gates as we scale the power supply voltage or VDD. We see that pulses show a lower variance, especially at lower values of VDD. And the table here shows the FO4 delays for a standard cell library of pulse gates that are laid out in 130 nanometer technology. So that's the FO4 delay, and that's the standard deviation of this library in the presence of process variations. So this table here shows the performance of pulse gates in different technology nodes. In 130 nanometer, we can create pulse gate delays that are 30 picoseconds, pulse widths of about 50 to 60 picoseconds. And for a serializer deserializer pair, we can have minimum bit to bit time of about twice the pulse width, which is 130 picoseconds, which leads to a maximum data rate of about 7.7 gigabits per second. So here we are achieving performances close to custom analog circuits by using a standard cell library of pulse logic gates. And the design flow here is a mostly digital style design flow. And further in a technology like 22 nanometer, we can achieve data rates as high as 25 gigabits per second for a serializer deserializer pair, again using a standard cell library of pulse gates. We will now present examples of high performance IPs that can be designed using pulse logic. The first example is that of a pulse mode asynchronous serial link. So our group at UCSB created 5 gigabits per second radiation hard links for CERN, and this was in 130 nanometer technology. These links use the same two-wire pulse signaling that we described earlier. And now we'll go over the design of different elements of this link. So at the transmit end, we have an 8:1 serializer, which serializes 8 bits of parallel data. And and the 8:1 serializer consists of serializer cells, where each serializer cell accepts a clock input or an enable input, which are events, either from the external environment or from the previous serializer cell. And each serializer cell first passes forward the serial output of the previous cell, and then after a certain delay, it serializes its own data input. So essentially, every serializer cell is adding a pulse to the serial data stream. And these are two 4:1 serializers shown here, one triggered on the rising edge of a clock and the other one triggered on the falling edge of a clock. And we finally merge the outputs of the two 4:1 serializer blocks to create an 8-bit serial stream. At the receiving end, we first have an 8:1 deserializer, which is constructed using a tree of 4:1 deserializers, which in turn are constructed using a tree of deserializer cells. And here, the deserializer cell, what it does is that it first merges the 1 and 0 data streams that it receives. Then the merged output drives a toggle latch, and the output of the toggle latch is used to split the original 1 and 0 data streams into even and odd number data bits. So we go on doing this splitting until we have just one serial output at the output of each deserializer cell. And we can construct an n-bit deserializer using a tree of deserializer cells where the depth of the tree is log n. Before the deserializer, we have a receive amplifier, which is also a pulse buffer sized so as to amplify the incoming pulse, which is about 500 millivolts. It is ground referenced, so there is no ideal power dissipation. Since it's ground referenced, this allows the receive amplifier to be used as a switch rather than a linear amplifier. So these are some of our measurement results. We could construct an entire triple modular redundant link in 130 nanometer, which ran at 5.1 gigabits with a total power consumption of less than 60 milliwatts. The layout footprint was really tiny. And the most important feature was that it was designed hierarchically from a standard cell library of pulse gates, which makes this design strategy very easily scalable. We will now describe the collective dynamic properties shown by pulse gate circuits and how these properties can be utilized for designing high precision multi-phase oscillators. So pulse oscillators can be constructed by creating loops of pulse gates. We call these oscillators collective pulse oscillators because of collective dynamics shown by pulse gate circuits. So pulse gate circuits have a property where the residual charge on the critical node stores memory of the past state, and this results in interesting dynamics. The timing diagram shown here illustrates how such dynamics arise. So V in here is the input waveform for G1. On the arrival of input pulses, the same cycle is repeated where the critical node is first pulled down, causing a rising edge on the output node, pulling down of the reset node. Finally, the critical node is pulled up, a falling edge is created, and when the reset phase of this gate is about to end, the reset node starts charging up to a high potential. However, if the next input pulse occurs at a time where the reset phase hasn't completed fully, both the pull-up PMOS transistor and the pull-down transistor will be turned on. And there will be a fight going on between the pull-up and pull-down transistors to charge or discharge this critical node, which essentially delays the second output pulse corresponding to the second input pulse. So the gate is showing repulsion. And if the input pulses happen to occur too close in time, because of the fight between the pull-up and pull-down transistors, the output pulse will be delayed. So we represent these dynamics in a delay separation curve, which plots the forward propagation delay of the gate as a function of tau, which is the relative separation between consecutive inputs to that gate. So we represent linear delay separation dynamics on this curve, where m is the slope of the delay separation curve, b is a constant, which is the y-intercept. And for repulsive dynamics, as shown by pulse gate circuits, the value of m is negative. The delay separation curve of a typical pulse gate actually looks like that. It's a bilinear curve, and it shows three distinct regions of operation. Region 1 is where the separation between input pulses is too small and the gate ends up rejecting the second input pulse. Region 1 is not the region of interest when designing collective pulse oscillators. Region 2 is the region of high repulsion, where the second pulse arrives at a time when the gate is starting its reset phase. So the output pulse is delayed substantially, and the delay separation curve shows a high magnitude of the delay separation slope. And region 3 is again a repulsive region, but the magnitude of repulsion is much smaller. And this happens when the second pulse arrives at longer separations, when the reset phase is nearing its conclusion. So due to the charge stored in the keeper node of a pulse gate, the next arriving pulse is delayed only slightly. So in order to tune the dynamics of the delay separation curve, we can either change the number of inverters in the feedback path. This will essentially shift the delay separation curve along the x-axis. And if we want to independently control the pulse width, we can use this secondary circuit in this block. And we can also change the relative strengths of the pull-up and pull-down transistors. This will change the delay separation slope. So one of the most important properties of these oscillators is that we can set these oscillators to operate in multiple stable modes by injecting multiple pulses at startup. And all of these different modes are stable modes of operation. Because these oscillators exhibit repulsive dynamics, if we inject K pulses at startup, these K pulses will distribute themselves uniformly around the ring. And we can create these CPO loops with both even or odd number of pulse buffers, because there's a double inversion that happens internally inside every pulse buffer. So CPOs can generate both even or odd number of clock phases. And the duty cycle for this oscillator depends on the width of pulses versus the total period at which the oscillator is operating. And the relationship between the number of gates, the number of pulses that we inject at startup, and the number of phases that this oscillator exhibits is very interesting. This again arises from the observation that pulses distribute uniformly in time around the loop due to repulsive dynamics. And this makes it possible to have a precise phase step at each gate of the CPO. So a CPO loop constructed using G pulse gates and initialized with P pulses. So if G over P happens to be an integer, we will see G over P different phases in the loop, and each phase will be available at P different gates. So we will see mirror copies of each phase. And more interestingly, if G and P are relatively prime, each gate will produce a unique phase that has a period equal to G over P times the forward delay of every gate. And the phase resolution will be the forward delay divided by P, the number of pulses. So by choosing G and P to be relatively prime, we can actually create phase resolutions which are much smaller and a fraction of the gate delay. So this helps us achieve very precise phases even in older technology nodes. So for noise analysis of these oscillators, we have derived an analytical expression which describes what happens in the oscillator if we inject an impulse of timing noise. So xk here is the arrival time of the kth pulse at one of the gates of the oscillator. Then we inject an impulse of timing noise, which is some epsilon in its value. And we see how the noise progresses over time. So when we plot the arrival time of the kth pulse, the solution here derived using a set of linear difference equation shows three distinct terms. The first term just corresponds to the period of the oscillator. The second term shows how much residual noise is left in the loop when we started with a noise of magnitude epsilon. So if M happens to be negative, which is the case in pulse oscillators, these oscillators show the behavior that the residual noise after several cycles is a value smaller than the noise that we injected initially. So we are left with a fraction of residual noise after several cycles. And then we have a transient term in this expression which decays to 0 as k becomes large. So again, xk here is written as the sum of the period of the oscillator plus phi of k, which is the remaining noise in the oscillator at k cycles. So we see here that the phase error is inversely proportional to the number of pulses, and it is proportional to a rapidly diminishing transient term. So if we inject multiple pulses in the oscillator, the amount of residual phase error left in the loop would be even smaller. If we increase the number of gates or the magnitude of the delay separation curve, we can reduce the amount of residual phase error in the loop. So this is a property which is unique to these pulse gates. Inverter-based ring oscillators, if they show no dynamics, which would mean that the slope of the delay separation curve is 0, an epsilon of timing noise injected in the loop would stay to be the same even as K progresses. So these oscillators are essentially showing noise correction over time, which is a unique property. So here we are seeing the behavior of the transient term of the expression in the last slide, basically the green term. So we simulated oscillators of different sizes, initialized with different number of pulses, and plotted what the settling time of the oscillator was as a function of the delay separation slope. Here we define the settling time to be the number of cycles taken for the oscillator to reach 1% of its final residual error, which is the value in the blue. So we see that for all multi-pulse CPOs, there is a critical value of M, which results in the lowest settling time. And beyond this critical value of M, as we increase M, the settling time grows. So we saw that if we increase M, the amount of residual error becomes smaller. But then if we go on increasing the magnitude of M beyond certain values, there will be a trade-off between the settling time and the residual phase error in the loop. So basically rings that have more pulses, more correction due to the repulsive dynamics, or a larger diameter will all take longer to settle. So far we've looked how these oscillators behave when we inject an impulse of noise, but we are more interested in seeing the behavior under continuous power law noise injection. And the metric that we use to evaluate the effect of continuous noise injection in time domain is Allen deviation. So these are Allen deviation plots for oscillators of different sizes, different delay separation slopes, and operating with different number of pulses. And modified Allen deviation is showing the noise. So the lower the value, the better is the oscillator. So we see that we see a region of initial instability, especially in oscillators that have a higher number of pulses or a higher delay separation slope. And this initial instability corresponds to the larger settling time of CPOs with a large gate count, pulse count, or delay separation slope. We see that beyond this high slope region of instability, the Allen deviation or the jitter stability of this oscillator is proportional to this term, which looks very similar to the expression that we derived for impulse noise injection. But this tells us that if we have equal pulse density CPOs, which means that the ratio of gates to pulses is constant, but if we scale the number of pulses, the power grows proportionally and the noise scales by the negative 10 log of P. So we have a square root of improvement of noise when we inject more power. And this behavior is very similar to that of coupled oscillators. And further, when we add more pulses to a CPO loop to increase the stability, we are adding more power, which is distributed in space. So we are actually increasing the frequency stability without increasing the power density of these oscillators. Here we are plotting a comparison of CPOs of different sizes with ring oscillators, which are powered similarly. And we see that in all the different metrics, such as RMS phase jitter, jitter stability, phase error, when you inject an impulse of noise, and cycle to cycle jitter in terms of power coupled noise, Similarly powered CPO oscillators perform better than inverter-based string oscillators. And finally, these are some measurement results on 8-gate and 40-gate CPOs that were fabricated in 130 nanometer. The footprint of these oscillators is very small, about 100 by 20 microns and 200 by 35 microns. And the 8-gate CPO could operate in 2 different modes with 1 or 2 pulses. The 40-gate CPO could operate in 10 different modes corresponding to 1 to 10 pulses. And we can use VDD to tune the frequency of these oscillators. We can also see that changing the number of pulses gives us a wide range of frequencies over which the oscillator operates. And another thing to note here is that the values shown in this column exactly match the analytical expression that we derived. So the measurements support the theory. And finally, for a oscillator where the number of gates and pulses are relatively prime, for example, the G equals 40, P equals 9 case, we have an oscillator which is operating at about 4.5 gigahertz, producing 40 different phases. So we are able to get about 5 to 5.5 picoseconds of phase resolution in a technology like 130 nanometer using this technique. So this is the end of the oscillator section of this talk. But we will glance over here the potential of multi-wire phase encoding strategies for designing very high bandwidth and low power on-chip communication links. And the high bandwidth and low power links that we'll describe here exploit pulse gate based circuits in advanced technology nodes. So here the objective is to describe solutions that allow high bandwidth data movement at low power on lossy and band limited wires across large scale chips. And multi-wire phase encoding is one signaling strategy that allows communication at bandwidths which are much higher than the bandwidth limit of wires themselves. So we achieve this high bandwidth by encoding data in the relative transitions on multiple wires. So these relative transitions can happen at separations which are much smaller than the bandwidth imposed by a single wire, and which is why we are able to transmit data at effective bandwidths that are much higher. And once again, here we encode data in the transition of edges as opposed to levels, which is done in normally NRZ encoded serial links. So since the data is transition encoded, it allows instantaneous data recovery without a sampling clock, a PLL or a DLL at the receiving end, which helps with both lower idle power dissipation and achieving a lower latency, as you're not spending any time in achieving link synchronization. And these are just some numbers to show the potential of this technique in a scale technology like 22 nanometer. So we simulated 6-wire multi-phase links in 22 nanometer. MWP stands for multi-wire phase encoding. We simulated single transition multi-wire phase encoded links which allow a single transition amongst multiple wires at any given point of time, and MMWP links which allow multiple wires to transition at the same time. And these links can achieve very high bandwidths on 6 wires in the range of about 70 to 125 gigabits per second across millimeters of wire, on-chip wire, where the energy dissipation is about 0.5 picojoules per bit to less than 1 picojoules per bit. So this is a very powerful technique for on-chip, chip-to-chip links for moving very high bandwidth data at low power.
Good morning. I'm David McCarthy, and I'm going to present on our work on verification of pulse gate circuits. So the objective of this verification work is that given correct schematics of a circuit, we wish to ensure correct layout, both from variation such as power or process, or also from systemic delays such as wire delay that layout would add. To achieve this verification, we take an approach of specifying the interfaces around the circuit with simple specifications and inferring the rest of this behavior of the circuit from the schematic and those interface specs. This contrasts with a lot of traditional asynchronous verification techniques where the entire behavior of the circuit has to be specified to achieve verification, or from something like the synchronous paradigm where the entire behavior is implied by the schematic. Having identified the correct behavior of the circuit, we then wish to build a timing constraint database sufficient to ensure that any post-layout behavior with variance is the same as the nominal behavior of the schematic. The strategy for doing this is first we define a unit time model that we will use to identify the correct behavior. Then we wish to ensure that the variance that builds up in the circuit is bounded and finite so that we can make timing guarantees at all. Having done this, we wish to identify points in the circuit where the timing variance that does build up could lead to incorrect behavior. These are hazards. We wish to put timing constraints to ensure those hazards don't happen, and we do that by tracing the paths that lead to those hazards. And lastly, we'll discuss ways that this methodology can be extended to larger circuits by making these guarantees across interface boundaries. So what are the timing hazards of a pulse gate circuit? Well, a timing hazard in general is where one event should happen after another, but they either get too close or they switch order. So one example would be a hold hazard. Here, a pulse is meant to coincide with the old value of a data signal that's about to change. The pulse happens later than expected, so it either comes as the data signal is changing and you get incorrect electrical behavior like a run pulse, or it comes after the data has changed and you get correct electrical behavior again, but different logical behavior than was expected. Another example would be a setup hazard, where a pulse is meant to see the new value of a data signal, but arrives early, so it sees the old value. And the timing constraints we wish to impose to avoid these hazards take the form of paths. Here we're considering a hold hazard at the input of the AND gate OR 0. The go pulse arriving at OR 0 is meant to see the old value of D0 when the go pulse arrives at OR 0. So we wish to ensure that's the case, we have to ensure that the path, the longer path, red path shown, that represents a change in D0 takes longer than the time for the go pulse to arrive at OR 0 plus the hold time of OR 0. To identify the nominal behavior of a circuit, we define this unit time model. And this is inspired by the fact that pulse gate circuits, the gate libraries we're building them on, have relatively similar propagation times. We fiat that we can take the bundles of pulses that result from these relatively similar propagation times and treat them as simultaneous. And this gives us an automata model, since we've effectively discretized time. A state of this automata model is a set of events happening at in the circuit at the same time that we're treating as if they happen simultaneously, and also the data signals at that same time. And then the next state in this model is if we propagate those pulses one topological step in the circuit forward, one gate forward, or if you prefer the guarded action view, one guarded action evaluation forward. So this is a picture of that. We have a pulse gate circuit on the left, and as we can see, a pulse propagates left to right in real time. That's equivalent to modeling this automata on the right, where effectively as the automata steps forward to its states, the one hot bits propagate forward through different state bits. For the unit time automata to be valid, we need three things. One, we need that the pulse gate libraries that we're building on have relatively similar propagation times, especially in the nominal case, and that's so that it captures the intended behavior of the schematic. The second property we need is that dispersion does not build up infinitely. If there's infinite dispersion in the circuit, all timing alignments might occur and we can't make any timing guarantees. To do that, we establish a property we call coherence on the circuits. And the last step is to ensure that the timing dispersion that does build up isn't sufficient to cause the malfunction of any of the gates. So here is the gate delay data that was presented earlier in the talk, but we have, by looking at a 5 sigma bound on it, made it into a bi-bounded delay model. Notice we've only done 1 sigma for the minimum time because these gate delays get long much easier than they get short. The coherence depth is a property we look for circuits to have to ensure that timing dispersion does not build up infinitely. It's defined as, given a set of events in the circuit that we're saying are simultaneous with our unit time model, how many unit time steps forward before the events in that new unit time step have a common ancestor from the first. That's equivalent to saying we can build up dispersion for d steps, where d is what we notate the coherence step, and then it will be absorbed by some mechanism in the circuit. So there's OR gates coalescing, that is 2 pulses arriving at the OR gate at the same time, producing 1 output, consensus gates, or paths simply terminating in latches or similar. And the smaller this coherence depth, the less timing dispersion can accumulate, but especially we need it to be well defined and finite for the circuit not to have infinite dispersion eventually. So this is a bound on what the coherence depth means. So if we have a coherence depth d for a circuit, then, and we have 2 events t1 and t2 that are the real times of events we're saying are in the same time step, the actual time between them is bounded by the formula shown. So for the gate library described, coherence depth of 5 actually turns into about 100 picoseconds of guarantee. So this is a relatively small number in the grand scheme of things, but it is enough that any design that was limited only by the coherence depth would have to be very conservative, kind of providing at least 3 gates of margin. So that is why we need timing constraints to do better. But to measure the coherence depth, we introduce this notion of a fast-slow labeling. So we take our automata model that we discussed below, we add labels, a 1-bit label to each signal that is occurring in a time step, and we say it's occurring fast if it's caused by ancestors that were fast, and it's caused slow if it wouldn't have happened if only the fast inputs into the gate, the previous gate are considered. This is shown here. To establish what the coherence depth of a circuit is, we can use this labeling by taking a set of events in the circuit that apply simultaneously, applying a labeling of them, a fast-slow labeling to those things, and propagating that fast-slow labeling forward until all the labels are either simultaneous or either all fast or all slow. The coherence depth is for all possible sets of events and all possible labelings applies to those. What's the longest until they become simultaneously labeled? So here we can see a set of 3 pulses, we're saying A, B, and C, that are occurring simultaneously in the circuit, and we've applied all 8 possible labels to them, and we can see that for all 8 cases, they do convert to the same value. In the longest case, it takes 3 gates to get to the same value. So this set of pulses evidences that the coherence depth is 3. We would have to check this for all other possible starting points in the circuit as well. This labeling effectively models and injected perturbations onto the initial pulses. So here we have the real times that might be associated with this labeling, slow or fast, that might correspond to the real-time labeling shown below. And then as we step forward through the circuit, we can see at later layers topological steps, the timing converges. So now that we've established that variance is not built up infinitely in the circuit, we wish to determine that the variance that does build up does not lead to incorrect behavior. To do this, we wish to impose further timing constraints beyond the coherence bound on the circuit, since that coherence bound is relatively conservative. To look at what hazards we might need to guard against, we can inspect the schematic of the circuit, and in particular look at pairs of gate inputs that interact at a gate and to see what hazards might exist. For example, a data signal and a pulse signal meeting at a gate input might lead to a setup or hold hazard depending on the order in which they are meant to arrive. To determine which of these possible hazards actually do occur, we take our unit time model and a BDD representation of it and test for sets of states in which certain signals exist. This is one use of symbolic execution in our tool. The other is the coherence step measurement is done by is done by bounded model checking. Having a BDD representation of our unit time model, we can look for the latest state in a path leading to a hazard, step back one state in the unit time model, and also step back by signal to see which ancestor led to the signal that caused the hazard, and tracing this back to a common ancestor will give us a path, and enforcing inequality on that path enforces that the hazard does not happen. So here we are interested in a hold hazard between signals D0 and go, which meet at R0. The same pair of signals, go and D0, also interact at S0, so we can actually just test for hazards between go and Z0, and say the same constraint applies both at S0 and R0. So to trace this path constraint, we first look at the states in which data signal D0 changes. Tracing back one step, we can see one possibility that leads to D0 changing is R0 in the previous step. Tracing that back leads to go. And for this short hazard, that's the entire short path of the short side of the trace as well, because the go is immediately there on the other side of the hazard as well. So we get the inequality that time from go to R0 to D0 has to be greater than time of go plus the whole time at gates R0 and S0. Tracing back differently, we can see that D0 could have been caused by S0 and again by go, so we get another path constraint for the same hazard. And both of these would have to be enforced to ensure proper timing is met. And more longer constraint can be seen if we consider the retrigger hazard at this OR gate, meaning that it's actuated twice in series and we want to keep those distinct. So the second actuation is this is in a completion tree, so it's on the second go pulse, the done zero resulting from that traces back to S0 to the second go pulse, and then tracing further back in time, we get that S1, which is the other side of the hazard, was caused by R0, which is caused by go, the earlier go pulse. So we get the inequality that time from go to go plus time from go to S0 to done zero must be greater than time of go to R0 to S1 plus the retrigger time of the gate done 0, 1. So if we apply this tracing procedure to all the hazards possible in our circuit, we will generate a database of paths, and provided all those paths inequalities are satisfied, the circuit should function as designed. Note that the hazard generation generates superfluous hazards. So here there's a coalescence hazard generated just by the typing, since we have two pulses meeting. To break the circuit up into regions, we specify the communication between those regions, then apply the existing analysis within each region, and then resolve the communication relation hazards. So the first reason we might want to break a circuit up into regions is if it proceeds independently. Here we have two iterative circuits which do not communicate while they're running, and thus might run for a long time independently and not exchange timing information during that time, and then finally agree at a consensus gate. It would be very conservative to analyze the whole system using a coherence depth argument, since it would give a very high number since they proceed independently, whereas if we analyze them separately, we would get a reasonable coherence depth for each, and we will assume that or analyze separately to show that the output combination is well founded, is well designed. The other reason is structural. So here we have a SERDES, and it might make sense to analyze the serializer and the deserializer separately, both because it will make the timing constraints produced make more sense, and also gives a behavioral check that the serial word looks like what we expect a serial word to look like. So if we describe communication in pulse gate systems as in terms of phrases, a phrase is a unit-timed regular language description of the communication. Having a set of phrases as our specification, we can divide this circuit into regions based on the phrases. Then we can evaluate the nominal behavior of each region by using the input phrase language as a generator into that region. And we can also check that the outputs are producing the phrases we expect by using the output phrases as recognizers. So this is an example of the phrase of a 4-bit word from a serializer. The SIR0 or SIR1 represents 1 hot bit encoding, and then the semicolons mean 5-bit gaps between each transmitted bit. Below, we can see the same thing expressed as a bubble chart. In addition to the serial word phrase, a deserializer system would have a go phrase at the start, describing the arrival of input data and the clock pulse to the serializer to start it going. And the deserializer would have a done phrase of it setting up its output word and signaling to the successor logic that that word is now received. Based on these 3 phrases, we can cut the system up into regions. So the serializer becomes the region associated with the go phrase input, and the deserializer is the region whose input is the serial word phrase. Now we need to extend our coherence depth argument to apply across regions. This is necessary since timing dispersion in one region will affect how much dispersion there is in the following region. First, we can measure the output coherence depth of a region much as we measure the coherence depth overall in the region, but considering only the output signals rather than all signals for our same label criterion. This may give a smaller coherence depth for the output phrase than for the region overall, since we are considering only a subset of the signals. Having established the coherence depth of the phrase as generated by its previous region, we can now establish the coherence depth of the region the phrase is leading into by generating arbitrary labels for the first coherence depth number of steps of the input into the successor region when we do our coherence depth analysis, and then settling to one value after that input coherence depth has passed. Doing this will give the coherence depth of the successor region subject to the input variance we saw in the previous region. Since the coherence depth of regions influence each other, we search for an overall equilibrium by starting out assuming that they are all 1 and iterating until an upper fixed point is reached. If 1 is not reached, then dispersion can build unboundedly between regions in the system. The other place we have to extend our arguments to deal with regions is for path tracing. Here we have a setup hazard at an AND gate between the toggle in the this is a deserializer, the toggle routing which way the next bit will go, setting up, and the arrival of the next bit to the AND gate. Tracing that back in the deserializer region leads to a path constraint that depends on the time between two different input bits. So to work out what that time is, we then have to set that pair of input bits as a possible hazard to be traced in the serializer region, and trace that as we would any other hazard, and that will give us a path constraint on the times that lead to those bit times, which in turn tells us whether the setup constraint in the deserializer region is satisfied. Having built tools to analyze circuits in this way, we get the following results for some of the example circuits we discussed in the talk. We've analyzed here a 3-bit counter and 2 SerDes systems, a linear and a tree-type serializer with a tree deserializer, and these numbers are from analyzing the SerDes as a system together, even though they're presented broken down per region. As you can see, we get a typical coherence depth of 4 or 5. If we break the number of constraints down per type, we'll see that different kinds of circuits have different kinds of constraints primarily. The counter has a wide balance of constraints. The serializers, because they're recurrent structures, have lots of retrigger constraints. The through constraints are the constraints propagated back from the deserializer that must be checked in the serializer. And then the deserializer has a lot of setup and hold constraints. Runtimes for this tool are about a minute for a SerDes system, and the counter is about 4 seconds. These are, however, based on a very unoptimized current version of the tool. Previous versions that did most of the analysis shown here, but didn't deal with region boundaries directly, could analyze each region in about 5 seconds. So we have reason to believe these numbers could be optimized significantly down to about 10 seconds for a SerDes system. Now that we have a tool that generates time constraints, aside from checking layout, another use for it might be to do architecture studies. So here I have compared a tree and a linear serializer in system and seen how long the path lengths we get are. This is a histogram of number of paths of different lengths. So we can see from this that the tree serializer looks to have hazard paths that are about 1 step shorter than that of the linear serializer. And further, the coherence depth is also lower, 4 for the tree versus 5 for the linear. This all suggests that the tree serializer might be a better architecture. However, that turns out not to be the case in practice for this particular pair of examples, because the linear serializer is a lot easier to lay out. So this technique may apply directly to some other examples, though for this one we probably want a more sophisticated metric to inform a decision. So in conclusion, we've defined a unit time model and shown how it allows us to identify the nominal behavior of a pulse gate circuit. We've shown how pulse gate circuits have this coherence step property that limits how much time invariance can build up. We've shown that for the
basically the high power overhead. There's no need to glitch. You have simplified latching in the design because, again, self-timing is walking along. You don't have to worry so much about where timing sources are. Local feedback provides stability against variance. That provides you with a little better global variance picture for how the gates operate. The gates have very wide operating voltage, so they're suitable for constructions in quite a variety of chip styles and designs. Practical performance is substantially higher than statically clocked CMOS. We've shown that in the previous slides. Collectively stabilized timing methods are available, which is kind of nice. It means you can build things at sufficiently high power densities. You can get all the parts of your distributed network contributing to the stability of your timing measure. So for timing distribution, for sync recovery, finite state automata on sampling, maybe timing for ABCs, certainly timing for links and sensors, IP with other critical timing needs. This technology seems like a very well-suited, appropriate technique. It's not a panacea. Logic power density is pretty high for for pure combinational blocks. If you're doing just large computation, it's better to wrap that in bits of this logic on the outside for control. Wire density is also fairly high because it's multi-rail, and wire sizing is fairly high, and you have to keep the wires apart from each other when they're running long runs because of coupling issues. Timing verification needs custom tools as well. The operating voltage range is indeed rather large. This is a plot of transmit versus receive SHMU for the original 5 gigabit link, and you can see that nearly a 40% range of available receiver voltages would operate the link properly at given transmitter voltages. It works well at low voltages. In fact, we've tested these circuits in the low 200 millivolts, stable operation. In fact, we've taken PCOs, pulse clock oscillators, down to 110 millivolts. We turned them to 600 millivolt modes and discovered that their modes were preserved. That's below voltage levels where our own external IP couldn't determine what was going on the chip. Energy scaling in 130 and 22. In 130, you've got access to about, well, almost 3 orders of magnitude in gate delay performance, and something, maybe two orders of magnitude scale in energy per pulse, available over the operating voltage ranges in 130. And kind of a similar but better picture in 22 FDX, gate delays down to 11 picoseconds for very high performance side, but quite usable gate delays in the 20 and 30 picosecond constructions at 0.4 of a volt, where your gate energy per pulse is on the scale of 3 femtojoules. So the scaling actually works quite well, and the access to low voltage regimes is pretty nice for these instructions. And the advantage, of course, is because they're self-timed, you can get stable functional clocks because the variance explosion isn't such a damaging proposition. It's asynchronous, but the composition rules lead to burst mode asynchronous. Things happen when you plan them on events because you're only allowing certain events to trigger gate operation. That means that atomic complexity is typically scalable. It doesn't look like factorial complexity. In fact, there's no essential hazards are possible. Current layer provides basically pulse timing sources for the next logic layer, which means that high performance is pretty accessible by simple pipelining tricks. Even though the gate delays themselves are a little bit longer than what you get in static logic, you can basically eat that back up by exploiting the fact that gate timing jitter is actually rather low, and you have local sources for that coherent timing. You have automated methodologies for time enclosure that's compatible with basically nice arbitrary asynchronous logic, so you can build large-scale systems where things are outside of the coherence range. You have arbitration, consensus, and feedback circuits to do that. And there's a pretty nice sequential verification strategy which does both timing and functional verification at the same time. And it's actually pretty easy to hook this up to conventional logic as well. For IP design, the benefits that you get are basically pulse logic gives you performance that's way closer to Fmax than you get for conventional static timing. Your time enclosure problems are substantially easier. You don't need you don't need PLLs and high performance clocks. You don't need to have low jitter clock sources for power as well. Timing margins are actually substantially improved, but of course it forces a functional decomposition about how you create new timing marks. And there's questions about what kind of generality that has for global design. We actually haven't run into problems that were that big of a problem that we could get it to sync. Event-based power lowers the use case power quite a substantial amount in practice, because it means that you can build things that have the potential for running extremely rapidly, but in fact, and in cases where things are running rather slowly, the slow event pulse sequencing means that gate timing is automatically governed to low rates. And you see that kind of same picture a lot, which is that you get high performance structures without having to provision timing and other sorts of things which continually use power. You basically get the power when you need it. You can easily build these designs in standard cells as long as you basically build appropriate wide wires to lower the dispersion. Pulses spread naturally across the functional loops, so peak power noise is substantially lower than conventional CMOS designs, which are synchronized. The design is understandable. The verification strategy handles FSMs as well as conventional logic. And the pragmatic path to realize high performance is pretty straightforward, to be honest. You can build bulk CMOS processes as NOx and things like that would be appropriate for this technology. In automotive BCD technology, you have high reliability CMOS design that can be made pretty accessible because of voltage issues, because of access to TMR, and SEUs that look just like pulses, and so that then logic can basically do sort of exclusionary voting just like you normally do. The other advantage of low powers is you can get low power sensor integration IP, and that's something that would be a good research topic to actually do in the future. And that's all we have.
Thank you very much indeed. I don't know whether you can hear me.
Yes.
Maybe we can have the speakers video on. Now, don't forget that only thing is the audience is on a completely different system. So there are 128 plus people who listen to your talk. I haven't got any questions from them yet, but they normally send me the questions to me a little later. But anyway, we'll see whether there are any questions. They might be a bit too shy, too early in the morning for us on a Sunday, perhaps. But in any case, I just wanted to find out. So I haven't been following this recently, but many years ago, I looked at pulse logic for asynchronous circuits. Is that now moving to sync? So is it the latest? The newer things are moving towards synchronous logic. Would that be reasonable, or am I making an assumption here?
I don't think it's an unreasonable assumption. Pulse gate circuits. Can I put it? These circuits are sort of pseudo-synchronous, I guess is the best way of saying it. They're self-timed. Right. The reality about asynchronous logic, you can control asynchronous logic and build wonderful things. People have done so. In fact, the earliest pulse gate circuits were like things like Milsom's work, right? That dates back to Lemartin. But the game that's a little bit hidden in those pictures is that there was an assumption that you could somehow make by fiat global time enclosure, which would be wire independent or gate delay independent, and then you could build things as big as you want and not worry about it. In one way or another, those ended up being kind of shell games to a degree. I mean, you either kind of hid the wire delay somehow, or you hid the gate delay somehow. Even the work of Chu, it never became highly productive to try to actually meet the performance guarantees without putting in some fiat of practical timing. And indeed, these circuits have such stable actual delays that it just makes sense to exploit that and treat them as effectively pseudo-synchronous elements. And then you can glom on all of the lovely CAD technology that you have for synchronous circuits, which I'm not saying that asynchronous is necessarily bad, to be honest, but it does remove a host of problems if you can build circuits which are self-timed and nonetheless can be treated as sort of pseudo-synchronous.
Right.
It makes your life much easier, right?
Yeah, debugging is always a problem, right? Always a much more difficult task, I guess. The other question that I had was, when do you think are there real circuits out there that are using these pulse circuits? Have they started? I mean, there might be some small things that must be around at least, right? I mean, or do they? What are the disadvantages otherwise?
Certainly, there are pulse gate-like circuits. If you look at the performance, for example, of the 32 gigabit GTX links that Xilinx now posts, you can kind of see that the switching technology there is beyond the ability of any FPGA. I mean, of any PLL to do. Right. I mean, how could you do that with it? And it isn't, right? They're hiding it under the covers. There's an actual asynchronous recognizer that's buried in that before you get to the switching that goes to the well-recognized PLLs. And the thing is that there's a number of circuits like that. I mean, Intel has been using asynchronous logic in a number of places as well. Not necessarily pulse logic. To be honest, pulses are kind of an anathema to CMOS designers because, after all, a pulse evaporates, right? And if you've ever done a lot of design, you just have a fear of that, right? But these circuits regenerate pulses handily. We've run practical things, as I say, down to low voltages, high voltages. I mean, and in areas like CERN, where we're beating on them with X-rays, and they still operate. They're not. It's not. Can I put it? It actually is a practical scheme for high reliability design. And in particular, in the radiation case, it actually even had the advantage that an SEU looked just like a pulse, which meant that you didn't have to worry about the whole reset side of the hidden SEU problem, which is that your logic does something untoward and gets stuck in a state that it can't get out of. Right here, you just see excess pulses, and you can play the standard TMR game, and then discover that that's actually a much more stable solution. So I won't say that there's a huge amount of stuff that's out there that does pulse gates. I'm not aware of it if there is, but in a certain sense, we're putting the tutorial together because it seems like India is a place where there's far more people to do smart things, honestly, than there is money to invest in really high-end technology nodes. And here's a methodology where a smart guy could build 50 gigahertz or 30 gigahertz kinds of links in bulk technologies, right? Which is something that otherwise you might think are actually impossible, right? So I think it was appropriate to push this in that direction. We're hoping people pick it up. I think you could do things like scope front ends, where much of your distribution logic is actually also being used to stabilize the actual input, stabilize the actual sampling of the front end of the scope, for example. That's something you don't normally get. Sorry.
Sorry, my knowledge is limited, but I just want to find out. There's some elements of ultra wideband communication similarity, the pulsing of data to communicate in this under the noise band. Is there any connection at all?
That's a really good question. I hadn't actually considered it in terms of ultra wideband. I got a colleague that does exactly that, and interesting.
It's just something that
I hadn't considered it, honestly, but it actually does make sense. The ultra wideband things, of course, are typically fractions of a terahertz in the very high end designs like that. I'm not sure whether the underlying technology here would make sense for that. I will say that the interest in NIST, I think, is things like cryogenic applications where you're talking to superconducting devices. So you've got very fast switching, and of course it's order independent, so you have to sample off the time, and you don't have any choice. And so there's a fair amount of interest of that. That's why Prashant is working at that area.
So quantum level switching and things like that. Would that be reasonable?
Yeah, absolutely.
So it doesn't look like the questions have come up to me. So I will ask all of you to send the questions to. Would that be okay? You'll be happy to receive email questions.
Absolutely.
I think there's some connection issues. So between the two things, the things are not coming to me. So I will ask them to send the questions to you. So and I thank all of you for being here, and thank you to the speakers for a very interesting talk, because I vaguely knew something about this, but I didn't completely know the details. So I got a lot of it out today. Thank you very much indeed, and I'm sure the participants would be extremely grateful. Unfortunately, they can't hear you, so I mean, you can't hear them. They can hear you, but you can't hear them. So on their behalf and on behalf of the conference, we thank you very much indeed. Much appreciated.
Thanks.
And we look forward to seeing you next year in person. Thank you.
Thank you, everyone. So we will have a short for 15 minutes, and we will start at 10:45 Indian Standard Time.
Thank you. Good night. For you, it's good night. So I'll say good night to all of you. Bye.
imagine. Advancements in 5G communications, autonomous driving, cloud, and hyperscale computing are delivering a deluge of data, offering compute challenges for those most able to adapt. Strategic thinkers are embracing tomorrow's challenges today. The visionaries, the disruptors, the architects of possibility. They see that integration and intelligence will be designed into the products of the future. They know the industry demand for holistic system design, for mobility, hyperconnectivity, performance, and reliability. The path forward will not be easy. You will need a trusted partner who can help get you there. Someone with the breadth and depth of technology to anticipate what's ahead. A company with the right combination of tools and expertise to empower you to create the products of the future. Go on. Unleash your imagination.
Memory is the heart of industry, making precision agriculture more productive, vehicles more autonomous, and smart homes more convenient. It is the heart of consumer experiences, making esports more active and VR more interactive. And it is the heart of AI, enabling it to do everything from make us coffee to make us laugh. At Micron, accelerating intelligence is more than a science. It's a passion, which is why we've assembled more than 37,000 thinkers and doers in over 18 countries who know that innovative memory solutions are essential to our future. A promise to continue pushing the limits, shaping the way we live, the way we work, the way we see the world. Memory is at the heart of what makes the impossible possible. And we are the memory makers. Micron. Intelligence accelerated.
is growing. In this changing India, design and manufacturing in semiconductors and electronics are important activities to boost its economy and meeting local consumption while being globally competent. Government of Karnataka, KTech and IESA together formed Semiconductor Fabless Accelerator Lab, a KTech Center of Excellence for Fabless, an initiative for developing and strengthening the fabless ecosystem in India. Suffle focuses on companies in semiconductor domain with their abilities to work on ICs and IPs. Suffle provides full access to expensive EDA and other tools and limited support towards MPW silicon tapeouts. Suffle also helps in mentoring, aggregated partner offerings, raising funds, aligning go-to-market strategies and various needs. Suffle initiative is much in line with the overall goal of Atmanirbhar Bharat. Potential in semiconductor industry is huge and Suffle helps explore the best of the possibilities. Located at MG Road, Suffle is easily accessible to all. Apply to Suffle program all round the year. Come, let's explore.
We'll rise up from the dust. Oh, here we go, go, go. Let us heal and grow. You won't be alone. We're unstoppable. Don't be afraid to show what we're going for. This is what we know. We will come back to life. We're still breathing. Standing up, everybody's gonna see it. Oh, all you need to know is that we're holding on. Even if we fall, we will rise up and we find the path that we believe in. No, we're not gonna stop until we reach it. All you need to know is that we're holding on. We rise up from the dust and clean my throat. We rise up from the dust. reasons why we are on this track. Oh, we all have our burdens, yeah, but we just keep on fighting up, we never look back. Here we go, 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 let us heal and grow. You won't be alone, we're unstoppable. Don't be afraid to show what we're going for. This is what we know. Here we come to life, still breathing, standing up, everybody's gonna see it. Oh, all you need to know is that we're holding on. Even if we fall, we will rise up and we follow the path that we believe in. No, we're not gonna stop until we reach it. Oh, all you need to know is that we're holding on. We rise up from the dust and claim our throne. We rise up from the dust and claim our throne. We rise up from the dust and claim our throne. When you feel it's hopeless, when you think that you lost, oh, I will take your hand and we'll rise up from the dust. Oh, here we go, 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 let us heal and grow. You won't be alone, we're unstoppable. Don't be afraid to show what we're going for. This is what we know. Here we come to life, we're still breathing, standing up, everybody's gonna see it. Oh, all you need to know is that we're holding on. Even if we fall, we will rise up and we follow the path that we believe in. No, we're not gonna stop until we reach it. Oh, all you need to know is that we're holding on. We rise up from the dust and claim our throne. We rise up from the dust and claim our throne. We all have our reasons why we are on.
Vous allez suffire à l'instant.
Tu es trop grand pour comprendre des choses aussi petites.
Technology. It makes us think of numbers, data, analytics, and math. All the stuff that goes on in our head. But the truth is, the head is powerless when it's not fueled by the heart. And memory is the heart of technology, the driving force that pumps life into every product, application, and innovation it touches. Memory is the heart of science, allowing researchers to explore the microscopic detail of the human body and the infinite grandness of the universe. Memory is the heart of industry, making precision agriculture more productive, vehicles more autonomous, and smart homes more convenient. It is the heart of consumer experiences, making esports more active and VR more interactive. And it is the heart of AI, enabling it to do everything from make us coffee to make us laugh. At Micron, accelerating intelligence is more than a science. It's a passion, which is why we've assembled more than 37,000 thinkers and doers in over 18 countries who know that innovative memory solutions are essential to our future. A promise to continue pushing the limits, shaping the way we live.
So, welcome. It's my pleasure to introduce the speaker for this tutorial. So, the tutorial is advanced delay calculation and variation modeling techniques for lower nodes and voltages. So, I'll just repeat the advanced delay calculations and variation modeling techniques for lower nodes and voltages. So, the speaker is Ratnakar Goyal from Cadence Design Systems. So Ratnakar Goyal is currently working as a software architect at Cadence Design Systems. He works in the areas of delay calculation with special emphasis on SOCB and advanced delay calculations. He has joined Cadence in year 2000 and has been working in timing library, static timing analysis, statistical timing analysis, clock tree synthesis, parasitic extraction, delay calculations, and crosstalk analysis, etc. He has published international conference papers, and he has been granted several US patents. So he did his master's in engineering from Indian Institute of Science, Bangalore. So I'll not take much time. Now Ratnakar will may start the tutorial. I will play the video, and after the video, Ratnakar would be available for questions and queries.
Hello everyone, welcome to this talk on advanced delay calculation and variation-aware modeling techniques for low nodes and voltages. We all know that static timing analysis is used to ensure that the chip operates at the desired frequency to meet the desired constraints. And the accuracy of static time analysis would in turn be dependent on the accuracy of delays it uses for the various design components like the gates and the interconnects. It becomes important to have, again, advanced methods are required for delay calculation. So the agenda of this talk is that we will start with the basics of delay calculation. We'll have a short Q&A break. We'll then look at the variation with static time analysis methods and modeling techniques. We'll then again have another short Q&A break. Finally, we'll talk about the advanced delay calculation methods required for achieving the accuracy at the smaller technology nodes, and finally we'll have another Q&A session at the end. So, in the first part of the talk, which is basics of delay calculation, we'll start with the terminology. We'll look at various gate delay models, and then we'll look at the various techniques which are used to compute the base delay. We'll then move on to look at the impact of crosstalk on delay and the role of timing windows and slews on crosstalk delay calculation. We'll then look at the different methods of attacker selection or attacker filtering, we should say, and finally how the crosstalk delay calculation is performed. So on this slide we have a driver cell and a receiver cell, and both of these are connected with an RC, which we call the load. So we define the stage as starting from the input of the driver cell to the input of the receiver cell. And the cell delay is computed between the driver input pin and the driver output pin, while the net delay is computed from the driver output pin to the receiver input pin. And the sum total of the cell delay and the net delay will be referred to as the stage delay. Now, the slew of the transition time is measured at specific thresholds on the waveforms at different nodes of the circuit. So, for example, over here, if we say this is my slew threshold, upper slew threshold, this is my lower slew threshold, then the time it takes for the signal to transition from the upper slew threshold to the lower slew threshold is the transition time for the particular node. So in this case, this is the, we have, this is the transition time for the driver input, while this is the transition time of the receiver input. So gate delay models have evolved a lot over a period of time. So we'll not talk about the very primitive ones, but the most important ones which are still in use. So the first one, which is the most commonly used, is a nonlinear delay model, which models the delay of a gate as a two-dimensional or a three-dimensional table. Well, one-dimensional and scalar tables are also possible, but the most commonly used method is modeling is a two-dimensional table, which has two indices. Index 1 is generally the slew, and index 2 is the load. And the way the data of the table is organized is that each row corresponds to a fixed value of index 1 and different values of index 2. So for example, over here we have, if you want to look up at the delay for 0.9 input slew and 0.002 load, then we go to the 6th row and look at the first entry of the 6th row, which gives us the delay for this particular pair of 0.9 and 0.002. So the next model which evolved after nonlinear delay model, the NLDA model, is the composite current source model, which basically models the current at the driver output for different times, and a different IT waveform is modeled for each load slew combination. So we have, for example, over here we have 3, 6, 7. Here we have an 8x8 table. So likewise, you would have 64 vectors of the current source model, the current table. And each of them would represent the current for a given pair of slew and load. So index 1 over here would be slew, index 2 would be load, and index 3 would be the time. And the values would be the current at each of these time points. The reference time over here is the time at which the input voltage waveforms crosses the delay threshold. And this is important in the sense because when you want to compute the delay from this current model, you need to integrate the output current to come up with the output voltage waveform. And once you have that output voltage waveform, then the difference between the delay threshold of the output voltage waveform and the reference time would give you the delay for the particular arc for a given load and slew combination. Then the next model which is used is the composite current source noise model. And so the noise model is basically modeling the DC current of the gate. And the way it is captured is that you apply a voltage source at the input pin and you apply a voltage source at the output pin. And then you compute the current flowing through the output of the output voltage source for different combinations of input voltages and output voltages. So in this case, we have these numbers are not representing the true value. These numbers are representing the voltages, and these values are representing the DC current values for different voltage combination pairs. Traditionally, these DC current tables are modeled from minus VDD to plus 2 VDD, but that's not the normal instance. Over here we see this minus 0.4 and it goes up to 1.8, where VDD is 0.8 volts over here. So the different delay calculation methods are the lump load method, the CFEB method, or the simulation-based method. So the lump load method is used in the readout stage where you don't have parasitic information available. And so that's the simplest form of delay calculation that can be done. And what you do over here is you compute the pin capacitances of all the receiver pins connected to the driver cell and use the C total to look up the NLDM table. And we would also need the transition time of the driver input waveform. And once you have the driver input transition time and the C total, you can look up the table to compute the delay for the particular arc for that condition. Then the next is the CFEB-based computation, which is which was primitively used, or it is used for low RC cases. And so there are different techniques of computing the CFEB. Some of the techniques are based on closed formulae or closed analytical formulas, and some of the techniques which are more advanced in nature would use an iterative method to compute the CFEB. So irrespective of the way you compute the CFEB, once you have computed the CFEB, then you use the same method as you use this lump load method to look up the delay from the non-linear delay table. Then the next method is the simulation of distributed RC. So this is the most widely used and probably in computation as well. So the various steps in this technique that you load or you read the RC from the spec file, and then you simplify that RC using a model order reduction tool, that would give you a lower order model. So in reality, your wire might be in the form of hundreds of capacitances and hundreds of resistances. But you really don't want to solve a circuit with 100 R's and 100 C's. So what you do is you feed in that RC to a model or DC, and it would give you a reduced model, which say it could be a pi model or a higher order model. And the choice of the model would depend on the kind of accuracy you want to achieve with that reduced model. So the higher the order of the reduced model, the better is the accuracy. So once you have that reduced model available, then one can solve ordinary differential equations to compute the gate delay and the net delay. And to solve this, to solve these ordinary differential equations, one would use numerical methods and would use the information or the data coming from the current source model or the CCSN models to compute the responses. And since we use the CCS time and the CCSN model, the gate delays are computed based on the receiver output waveform. So the driver output waveform is computed with this while solving these ordinary differential equations. Next, we move on to the factor noise on delay. So, since the wires are close to each other, and so they have an inbuilt coupling in the wires. And because of coupling between the wires, the transition on the adjacent nets would cause an impact on the delay of the net, which is currently being analyzed for delay compensation. So, in terms of terminology, we would call the victim net as the net for which we compute delay, and the aggressor net is any net which is coupled with this net. So, for example, over here we have this net as a victim net which is coupled with this aggressor A1, and the input of this victim is falling, which means that this victim has a rise transition, and the attacker is having a fall transition over here. So let's see what happens because of this fall transition on this rising output victim. So this is the input transition which is falling, and in the absence of crosstalk, we would just see this kind of response, a rising waveform at the victim net. Now, since this attacker is switching in the opposite direction, it has a fall transition, and these two nets are coupled to each other. So this falling transition does not allow the victim to rise as fast as it would have risen in the absence of crosstalk. So the victim then starts falling, and then it finally overcomes the attacker's fall transition and then starts rising again. But what happens in the process is that we create this kind of bump, and eventually the delay threshold is not achieved at the same time as it would have been achieved before in the absence of the attacker transition. So we have an increase in delay on the victim net because of the attacker switching in opposite direction. Now let's see what happens when the victim and the attacker switching in the same direction. So over here, this is again a fall transition of the victim input. And the green one would be the response of the victim had the no coupling. Now, since the attacker is also switching in the same direction as the victim net, which is both of them rising, and because of which this transition on the attacker actually makes the victim transition faster, and hence it helps in reducing the delay of the victim. So, opposite switching, the aggressors cause an increase in delay, and aggressor switching in the same direction cause a decrease in the delay of the victim net. Now, the windows are used, timing windows are important to ascertain whether an aggressor could actually cause a speed up or a slowdown of the victim. Because if my attacker is not switching at the same time as my victim is, then even though the two nets are coupled, the attacker switching will not have an impact on the delay computation of the victim net. But the completely timing windows is a tricky thing because timing windows depend on the delays of the fan-in cone, but the delay computation itself is dependent on the timing windows. So it's kind of a chicken and problem. And the way it is solved by most commercial tools is that we go in for an iterative approach. So one can start with one can assume infinite windows to start with that attacker can cause crosstalk delay impact on the victim independent of the timing windows. And then in that case you would compute the worst case crosstalk delay. Once you compute the crosstalk delay in this manner, using infinite windows for the victim and the aggressors, then you have some form of timing windows which can be built up. And then you can use those timing windows to refine the delays for the victim again. And this iterative process can be computed until there is no change in the time windows or the delays of the victim and the aggressor nets. Typically, this process converges in 3 to 4 iterations, but most commercial tools generally use a 2 iteration process because the convergence is still not there, but the percentage reduction which is achieved by adding extra iteration which would incur extra runtime is not significant to carry out an extra iteration. And again, these clues are important for both the victim and the aggressor to define the overlap between the victim and the aggressor. Now, the attacker selection process depends on the timing windows, first of all, as we just talked about. So here we have a case. This is the victim timing window, this is attacker 2's timing window, this is attacker 1 timing window. So there are different modes in which you could consider the timing windows of the victim and the aggressor. So there's a pessimistic mode which is called the path overlap mode, in which you look at an overlap of the victim and the aggressor timing window at any point in the victim timing window. So for example, this is the complete timing window of the victim, and at this point, both the victim and both the aggressors can switch together. So in this mode, one would consider the full impact of attacker 1 and attacker 2 while computing the delay of the switch victim net. Well, but in reality, you don't know whether the situation will happen or not. And if you are really interested in the worst case timing, then one would just want to compute the SI delay or the crosstalk delay impact on the worst edge of the victim. So over here we have, suppose this is my critical edge of the victim. And if I look at this critical edge of the victim, then only attacker 2 is overlapping with it, while attacker 1 has already finished its transition to A4, the critical edge of the victim, right? So in this case, you would use a partial contribution from attacker 1 and full contribution from attacker 2 while computing the crosstalk delay. Then the second thing to consider for attacker selection is the cross relationship between the victim and the aggressors. So the timing windows concept is important for cases where the victim and aggressor are having a synchronous clock relationship between them. If the victim and aggressor have got an asynchronous clock relationship, then the attackers are considered to be fully contributing to the crosstalk delay of the victim, And if the attacker and victim are from physically exclusive blocks, then there is no crosstalk impact of the attack on the victim. So then logically correlated aggressors is another way of filtering aggressors. So for example, over here we have a victim which is coupled to these 4 aggressors, and if this victim is say rising, then we know that attacker 1 will be rising and attacker 4 will be rising. But they might not be falling at the same time when the victim is rising. So for match delay computation, we know that attacker 1 and attacker 4 are logically correlated to this victim, and these can be filtered out without impacting the accuracy of the delay calculation, and thereby reduce the pessimism of the crosstalk delay. Likewise, A2 and A3 would not contribute to the min delay calculation. Then the last thing to consider is the unconstrained aggressor. An unconstrained aggressor is one for what we don't have time available. So there will be 2 approaches to that. These kind of aggressors. One is infinite time window, which is a pessimistic approach. Since you don't know time window, you can say that, okay, I'm going to consider an infinite window for this aggressor and do a pessimistic analysis, or you may say that, okay, I would assume that the aggressor is constant, and that would lead to an optimistic analysis. Now, so how do we compute crosstalk delay? So the crosstalk impact on delay depends on the victim slew, aggressor slew, the switching directions, and the arrival window, which we have all talked about. So for example, over here we have, so what we do is first of all determine the slews, and then you compute the attacker to victim delay, which is basically to say that, okay, how much time is it going to take for transitioning happening at the aggressor driver cell and the receiver input pin. We also call the time light. And once you have the time of flight available, then it's an iterative process to place the aggressors in such a way so as to maximize the delay at the receiver input. So one has to see what is the best case or the worst case delay that can happen because of crosstalk on my victim, and to achieve that worst case delay, one needs to sweep the aggressors such that the delay on the receiver input is maximized. And again, there are different methods in which this can be achieved. So the brute force method would be let the victim switch to various directions and let the aggressors switch in their respective timing windows, perform a simulation for different combinations of the attackers at different positions within the timing windows and compute the delay accuracy on the victim. And once you are done with this process of computing multiple delays for different combinations of the victim arrival and the attacker arrivals, you give the worst case delay to get the worst case victim delay. There are various methods and different techniques which different tools use to optimize this methodology for runtime. But there could be many other ways to do it. Okay. So to wind up the section, we'll look at timing report from test timing sign-up solution. So let's just talk about this report. It says met setup check with pin CF clock. So this endpoint represents the path endpoint, and it says that Okay, my path is ending at the CF instance, pin D, and there's a rise transition at pin D, and it is checked with a rise transition after the red clock. And my beacon point was the Q pin of instance LF. Again, a rise transition was there at it, at the Q pin. So on this part of the report, we have the net and the cell is the library cell name, then the instance name. Then we have the delay, which is the total delay. So over here we say that 277.9 is the delay of the arc from clock to Q. And the incurred delay for the clock to Q arc is 0. And 177 is the slew at the Q pin. And this is the load seen by the Q pin. Now if you look at this delay, the second delay is 164.3, and it also shows that the incurred delay is 163, which means that the base delay, so this is the delay, this delay is the total delay which includes this crosstalk delay or the incremental delay. And we see that almost the entire delay is coming because of crosstalk over here in this case. So this incurred delay is important in reporting so that one could probably reduce the coupling of this net to improve the timing of this path. Then the other things on this report are the other arrival time, which is the arrival time of the capture clock path, the setup time of the receiver clock. This is the clock period, which is referred to as phase shift. Then the CPR adjustment, and finally the required arrival and stacks. Here is an example of a delay calculation report from Tempest timing sinus solution. So it says that okay, from pin LF/Q, and the voltage of this pin is 0.92 volts. This is library cell. This is the name of the library from which the timing data has been extracted. This is the receiver pin, and it is also operating at the same voltage. And the receiver cell is a buffer cell. And it is coming from the same library case. And the report we are doing over here is an SI delay, and it is a net delay. Then we have the thresholds which are used to measure the delay, and thresholds for slew. And the slew period is again is a very modern technique. We don't talk about it right now. Then the next section is the RC summary of the net. It says that there is 3 capacitances. The total net capacitance is 70 FF. The total rise capacitance, which includes the pin capacitances, is 71.6 FF, and likewise the total wall capacitance is also around 71.6 FF. And the RC had 3 resistances, which in total of 30 ohms. Now this next section of this report tells us the SI information. This is the victim time window spans from, so this is for rise, and not put in the section for fall, which will be similar stuff. So the victim time window spans from 342.7 PS to 343.8 PS, and with respect to direct clock. Then this victim has one aggressor, which is N6, and it is a synchronous attacker. It is having a call transition with a slew of 140.399 picosecond, and the coupling capacitance is 39.999 picofarad. The attacker had a single fan out. It's operating at a 0.92 voltage, and its timing windows are 434 PS to 435 PS with respect to direct clock. And then the next section shows what kind of models do we have. So it shows that the driver instance is a CCS model, and the receiver instance is also a CCS model, and the attacker pen is also a CCS model, and then finally we have the encoded delays and the net delays, total net delays. This is the transition at the LF/Q pin, and this is the transition at the D1/A pin. So with this, we come to an end of the first part, and we will take a break for any questions you have, and I'll like to answer them. In this part of the tutorial, we are going to cover variation of static timing analysis. We'll look at what SOCV is and what are the library modeling requirements for SOCV. We'll consider the impact of inputs to variation on SOCV computations. Then we'll look at the concept of correlated path delays and uncorrelated path delays. We'll further look at the arrival computation, assuming that the stage delays are correlated or uncorrelated. We'll also have a look at the challenges in STA with SOCV and timing robustness analysis. We all know that the IC fabrication process has variations which can vary from wafer to wafer, die to die, or lot to lot. These variations have an impact on the delay of the fabricated components, whereby the delay of the fabricated components can vary due to these process variations. In order to ensure that the chip operates at desired frequency, designers need to sign off the chips at the worst case corner or the worst case delay corners. However, the worst case delay is going to happen only in few rare cases, and using this card padding technique of signing off the worst case delays typically leads to excessive over-designing. In order to circumvent this over-designing, single parameter statistical timing analysis, or SOCV, is being used these days. So SOCV can model the variation. SOCV can be used to model delay variations to variation as well as the timing check variations. And the modeling guidelines are as provided by the Liberty Variation Format or LVF syntax, and we'll have a look at the syntax in greater detail in the coming slides. In addition to the variation which is modeled in the timing lab in the LVF library, the impact of inputs to variation is significant, and that also needs to be considered for doing an accurate SOCV analysis. So how is SOCV different from STA? STA has discrete values. SOCV has got distributions. Discrete values are easy to propagate. Statistical values have got their own challenges of propagation and worst casing. Furthermore, the designers have been used to a discrete system of analysis. So they are used to having timing report which have got a single delay number, a single slew number, and a single arrival number. So adding more data or more fields to the timing reports makes the life complicated. So to simplify things for the designer, tools like Tempus timing sign solution, they allow the user to report either discrete values, which are the quantile values, or the statistical values, which would mean that the report would have separate entries for mean, standard deviation, and sigma. So the diagram over here is a classic Gaussian curve, and it just defines what is the mean value, what is the sigma, and what's the quantile value over here. So there are two types of modeling. So we'll first of all look at the early sigma modeling and the late sigma modeling in the library we have. So early sigma modeling and the late sigma modeling are done in a manner which is similar to the NLTM delay table. It's exactly the same format you got index 1, which is generally inputs to index 2, which is load, and then there are values for which correspond to each combination of load and skew, or index 1 and index 2, which is there in this tabular format. The keyword to look at is the sigma type early and the sigma type late. So the sigma type early signifies the early sigma, or the variation which is on the left of the mean value, and the late sigma is used to compute the late quantile values. Like NLTM tables, these are indexed by slew and load. Now then we have the LVF moment extension. So what is the LVF moment extension? The LVF moment extensions provide a method of modeling the mean shift, the standard deviation, and the skewness. So mean shift is the difference between the mean value of the distribution and the nominal value. The nominal value being the value which was characterized in the absence of any variation. Standard deviation is a measure of the dispersion, and it is a formal definition of the second order moment of the distribution provided by LVA. And the skewness is the third order moment which is modeled in the LVA moment extensions. We'll look at each of these in the coming slides. So mean shift is modeled as OCD mean shift, and then you would have cell rise, cell fall, rise transition, fall transition, and so on. Again, these are 2D tables indexed with slew and load. So here we have an example of a cell rise, which is table, and mean shift cell rise. So the timing report would have, the tempest timing report would have the combined effect of both these modeled as delay mean. So for the given slew and load, you pick up the cell rise value, and for the same slew and load, you pick up the mean shift value, add them together, and that's what gets reported in the delay mean column of the tempest timing report. Then you have the standard deviation of the second order impact. The standard deviation is basically a measure of the dispersion. A large standard deviation means that the variations are having a large deviation from the mean value, and a smaller standard deviation means that the samples have a smaller range of deviation from the mean value. So the delay and the LVF construct for this is OCD, STD, so OCD standard deviation, then you could have cell rise, cell fall, rise transition, fall transition, and so on. Again, this number gets looked up with the input slew and load and gets reported in the delay sigma column if the skewness is not there, or in the delay standard deviation column in the skewness propagation mode. So the third moment is the skewness, and the way it is handled inside the tool is that you look up the standard deviation value for a given slew load, and you look up the skewness value for the same slew and load. then these two values are then converted into an effective sigma value. Now, the way Tempest computes this effective sigma value is sort of proprietary, so I cannot talk much about it. But it is representative of the fact that a positive skewness means that the late quantile is larger than, or the late sigma is much larger than the early sigma, and likewise the negative skewness would indicate that the early sigma is much more larger than the late sigma. So when the skewness, the effective sigma is larger than the standard deviation. So then here we have this delay HTD, and this is the sigma value over here. Then the delay value is computed by mean plus 3 times the delay sigma value over here, assuming that the user is doing a 3 sigma reporting. Now the delay variation of a signal has two basic components. One is coming from the process variation, and the second is the slew-induced variation. The process-induced variations are captured in the library either using the early late sigmas or the moment extensions which include the mean shift, standard deviation, and skewness. However, the slew-induced variations are not part of the library and need to be accounted for separately. The simplest form in which the impact of the slew-induced variations on delay is computed is that to take the sigma of the input slew, multiply it by the variation in delay to minor variations in the input mean slew. So this component, which is delay by del slew, can be looked up from the NLDM delay tables itself. So you have the input slew mean and you have the input slew sigma. So input slew sigma is over here. Then you take the input slew mean and do minor perturbations to that slew. You'll get two different values for delay, or two different. So you get two different delay values for two different perturbed slews. Take the ratio, and that's going to give you this second component. And this overall impact is the impact of the slew-induced impact on delay. Now, depending on the sigma of the input slew, this impact could be significantly large. And what we observe is that this impact becomes larger at lower technology nodes, which means that there is a significant variation in the slew as well. It's not just the delay variations which is impacting, it is the slew variations which is impacting the delay to vary a lot as well. Now, correlation path delays. The stages along the path can be considered to be fully correlated, or they might be considered to be completely uncorrelated. And the amount of correlation would depend on different factors like cell types, loads, slews. However, because of the fact that the input slew sense has an impact on the next stage delays, so there is some amount of correlation which is always existing in the path delays. So in low accuracy mode, all variations are considered to be uncorrelated, whereas in high accuracy mode, the slew variation effect on delay is treated as fully correlated. Let's see what it means. So in low accuracy mode, we say that the delay variations of the instances of the path are considered as uncorrelated, which means that the arrival time computation is a simple RSS. So at this first instance output, the arrival time sigma is the same as the delay sigma of this first instance. Now the arrival time over here, the sigma for that is computed by using the input arrival RSS squared plus the delay sigma RSS squared of the second instance. Now when you go to the next instance, the arrival again is computed. The arrival sigma is computed using the input arrival sigma square plus the delay sigma square of the third instance, which is U3 in this case. And likewise, the entire path arrival is computed. So over here we assume that there is no correlation between the delays of different stages. Now what happens in case of correlated delays? So if we assume there is a correlation between the path delays. So the instance U2's delay would have two components. One is the correlated variation, which is because of the input variation, and then you have the uncorrelated variation, which is because of the parameter variation of the second instance. Now let's see how arrival computation happens over here. At first instance, since there is no input variation, the arrival time sigma is the same as the delay sigma. At the second stage, this equation is looks similar to the one we saw on the previous slide, but instead of having the AT1 sigma square over here, it is the AT1 adjusted sigma over here. So the way the AT1 adjusted sigma is computed is like this. That the AT1 adjusted sigma is basically the delay sigma for the first stage plus the slew induced delay sigma of the second stage. They're added together, assuming that they are fully correlated, and then you take square of these. Now, when you go to the next stage, third stage, the arrival computation becomes still trickier. Now, looking at the equation, they look very similar, but the 82 adjustment is computed differently than 81 adjustment square, in the sense that it is 82 square minus the sigma, the delay component of the second stage, the sigma component of the second stage, plus the correlated component of the next stage. So these are assuming fully correlated delays, and if you want to have, if one can actually come up with a partial correlation metric, then these equations would change accordingly. So having said this, all these computations are easy to do for 1 or 2 stages, but when it goes to more than 3 stages, it's probably much difficult to hand calculate these. Now the challenges with STA and SOCD is that of the max operation. STA needs to perform max operation for emerging, delay emerging parallels, and worst case arrival computation in graph-based analysis. So with discrete quantities, this max operation is pretty straightforward. You just do a max or a min, and you're done. But when you are dealing with statistical quantities, doing a max or a min is not that easy. Tempus has got a robust proven max operator which works well and which is bounding as well as not excessively pessimistic. So on this slide we have a 2-input gate, this NAND gate, and it's got 2 inputs N1 and N2. We've got the arrival times of these 2 input gates. Then we have the delays of the 2 arcs from N1 to out and N2 to out. And now the objective is to compute the arrival time at the gate output. How do we do it? So we have got all these pairs are mean, sigma, mean, sigma, mean, sigma, mean, sigma pairs. So if we were to compute the arrival time because at the output because of this 80 in one and delay in one dot, then the 80 out one would be 2381 mean and 119.4 sigma. Likewise, the 80 out 2 would be having a mean of 266.5 and a sigma of 105.3, which would lead to a quantile value of 582.3 over here and 596.4 over here. Now, in this option 1, which we are trying to discuss over here, if you pick the max or the worst mean and the worst sigma, then the worst arrival would have this as the mean sigma here, and the quantile value would be 624.7. So, which is more pessimistic than any of these. So, which is more pessimistic on than both the arrival times and his bounding. So, this operator would work fine in general, but the only concern over here is that it could be much pessimistic when this operation happens successively for multiple stages along the path. So what's the second option we have? The second option is over here. We have, it's the same example over here, except that the worst arrival is now computed differently. Now the difference over here is that we preserve the worst mean from the n arrivals, and then we preserve the worst quantile from the n arrival quantiles, and then use this worst quantile and the worst mean to come up with this worst sigma value for the arrival time, and then propagate it forward. So this ensures that we are bounded, but also ensures that we are not excessively pessimistic while doing the worst or the max operation. Now let's look at the concept of bounded slacks versus GBA slacks. Traditionally, one would like to see a bounded slack or the worst slack when you do a report timing dash to an endpoint. When the intent while doing a report timing dash to a particular endpoint is that I want to see the worst slack of all the paths which are coming to this T1. Now, in order to see the worst slack, the STA tool needs to consider the entire pan and cone of all the paths reaching this T1. So they could be coming from A1, AN, B1, BM, and so on, and they all reach T1. So, and whatever these clouds are combinational clouds, combinational logic clouds, and there will be multiple max operators which are happening in both STA and SOC, but since the STA operator is simple and does not have any pessimism, that works fine. But with the SOC, the max operator can change with the number of max operations happening. So when you consider this entire pan and cone, then you can see a worst slack. Then you'll see a worst slack to this endpoint T1. But now if you start doing a report timing from A1 to T1, from A2 to T1, and so on and so forth, you would see that none of these slacks probably matches the worst slack you obtained when you did a minus 2 T1. This happens only in the case of SOC, not in the case of non-SOC or normal STRs, because there is no max operator in STA, which adds pessimism, but in SOC, to ensure that we are bounded, the max operation could add some pessimism over there. So here is an example of what we really talked about. So the delays on these cell arcs are fixed, they are assumed to be the same for both the arms, and the interconnect delays are also there. Now when you do a report time in -2 out P, you get a slack of -40, 14.48, and but when you do a report timing from in A1 to out P, you get a slack of -14.368. So we call this as a bounded slack because it is covering the paths from A1, from A, B, and C, and D to come with output. But when you do a path reporting from A1 to output, then there is no merging happening along the path. And in this sense, you get a true GBA slack over here, whereas what you get over is a 2 PBA slack. And if you, even if you look at the reports over here, the path being traced is the same. And the delay mean and the delay sigma values are the same in both the reports, except for the fact that the delay mean and the arrival mean and the arrival sigma have started changing beyond this point. So what is the slack distribution? The slack distribution of path indicates that so many samples or chips of the path will be non-violating. So if this is my slacks graph with the slack quantile 0 and 99.865 paths being non-violating, it would mean that for 1 million chip samples, this particular path is going to fail in 1300 T of the chips. Now, if there are 10 paths coming at the same endpoint, and the slack of each path is an independent random variable, then the probability of each of them failing is the same as we see is 0.00135, and path probability of any one of them failing is 10 times, which is 0.0135. Now, if we consider 1 million such endpoints, then the probability of all of them having non-violating slack is 0.9865 to the power a million, which is 0. But in reality, the chips are working fine with a fairly high yield. And the reason for this is that the path and the endpoints are not independent, but partially correlated. And the computation which we carried out assumes zero correlation and hence zero probability of yield. So in order to come up with the better and accurate estimate of the paths which can potentially fail, one needs to consider the correlation between path and slack. Because paths to the same endpoint may have common stages resulting in correlation in the path slack. Now, computing correlation between endpoint slacks has quadratic complexity, and it's not easy to do. The timing robustness is a functionality provided by timing tempus, timing sign of solution for efficient accurate computation of the probability of failure in such cases. Here we have an example of Tempus SOC PBA report. So we have, if you look at the delay part of the report, we have the delay mean, then you have the delay sigma, delay standard deviation, and the delay skewness. So the delay mean includes the mean should part. This is the standard deviation from the library. This is the skewness from the library. And then using the standard deviation and skewness, Tempus computes the effective sigma. And then this effective sigma is used to compute the quantile delay, which is the mean plus 3 sigma delay in this case. Likewise, we have the arrivals over here as well. But at least for the sake of understanding, let's understand that these arrivals, mean, standard deviation, and skewness are not really, the delay, the delay sigma is not really very important because the slack is getting computed by the arrival sigma, and we are propagating the standard deviation and the skewness separately in PVA mode. So it is the arrival sigma at the end point which becomes important for the slack computation, and these are more from reporting and fixing perspective that these numbers are very important. They are not important from a slack computation perspective, the sigma values. Time for Q&A. In this part of the tutorial, we will talk about the advanced calculation techniques, which include waveform effect, implications of misscale, receiver pin capacitance, backmiller effect, multiple input switching, and airdrop analysis. Traditionally, data calculation has been using slew as a metric to compute the gate delays. And it's a worst case slew which gets propagated along a timing path in GPU, or the actual slew which gets propagated along a timing path in PVA. However, at lower technology nodes, this concept of slew is no longer relevant, and one needs to propagate the waveform along a timing path to get the same level of accuracy as one gets with transistor level simulation. For example, in this diagram we've got multiple waveforms which are the same slew, but they've got different wave shapes. And if you look at the delay corresponding to these different wave shapes, we see that there's a 10% spread in the delay for this particular gate for the different wave shapes. So we see that the wave shape has a profound impact on the accuracy of the delay numbers computed. Another observation which needs to be made over here is that the output of the gate is starting to transition only after the input waveform has reached the lower slew threshold, which means that the impact or the delay calculation or the delay of the gate is dependent on the shape of the waveform beyond the lower slew threshold in this case. So, or in general, we could say that it is more profoundly impacted by the tail of the waveform. So, capturing the tail, first of all, and propagating the waveform tail becomes imperative for the accuracy of delay calculation. Now, what happens in case we miss a tail? In case we miss a tail, we will become optimistic. But why do we become optimistic when we are doing a waveform propagation? Well, even when you are doing a waveform propagation, you still need to get data from the library. And the library is all modeled in terms of slews and loads. For example, if you want to get the pin capacitances, then you need the input sleeve. Or if you want to get the current from the current tables, then again it is indexed by the input sleeve. So in some form or the other, you still need to be relying on the input sleeve model in the library. Now the input sleeve model in the library is again not a ramp, but it is the sleeve of a pre-driver waveform which was used to characterize the gate delay. So for this example, we have a distorted waveform, and if we use a 3070 slew threshold for measurement, then we end up using this waveform. Then we end up using the data corresponding to this waveform from the library for lookup, and if we use a 2080 threshold, then we are using a better waveform which is representing the distorted waveform in a much more better way than the waveform corresponding to a 3070 slew threshold. So a wider slew threshold helps in capturing the tail effects in a better manner and is recommended to use 2080 or 1090 as the slew thresholds, so that even the implicit data which gets collected from the library based on the slew is more closer to what we want in reality. Now there are multiple challenges associated with waveform propagation. So if you look at the tasks involved are computation of an accurate receiver model, then you need to propagate the waveform from one stage to the other stage, and lastly you need to have a good driver model as well to consume that propagated waveform for delay calculation. Now look at the receiver models in detail in the coming slides. And if we talk about propagating the receiver waveform, since graphics analysis is done in a breadth-first manner, so one needs to store the waveforms for some time before we actually reach the delay calculation of the next second stage. And the simulated waveforms typically could have hundreds of voltage time pairs, and storing such huge waveforms for the entire design or a level in the design would require a lot of memory. So one has to resort to some kind of sampling methodology to sample the waveform in a pure set of points and then propagate it going forward. So the most intuitive way is to do a fixed grid sampling, which is easy to do. You can sample it, reconstruct the waveform easily, but it has got its pitfalls that it may miss the critical parts like pumps and tails. So the next best you can do is you go and for a variable grid. Now with a variable grid you can capture the tail and the pumps more effectively, but one again needs to be very precise in choosing the gate grid point so that the pumps and the tails are not missed. So that's the challenge with the variable grid. And another challenge with the variable grid is the reconstruction of the waveform, since you need to store some information on the waveform got sampled so that you can reconstruct the waveform when you are constructing the waveform from the stored samples. Now the receiver waveform is first propagated to the next stage. You need to have an accurate driver model which could provide a good delay calculation accuracy with the receiver input waveform. So if you don't have a good driver model, then even if your waveform is very accurate, you might not have the required delay calculation accuracy. So for that purpose, one might need to use a current-based model or a VO-based model. NLDM-based models will not work, for sure. Now if we talk about the receiver models, NLDM traditionally has been modeling the receiver pin capacitance either as a single value or as a single value for rise and fall and in some cases there are ranges also specified for the rise pin capacitance and the fall pin capacitance. CCS, on the other hand, has a more sophisticated receiver model, and it gives you the capability of modeling the pin capacitance for different segments of the waveform, corresponding to different slew thresholds, and different capacitance for different parts of the waveform. Then CCS has the capability to model the pin capacitance either at an arc level or at a pin level. The arc level modeling is used when you have a slew dependent and a load dependent function for the output capacitance, for the input capacitance. So the arc level models are there inside the timing groups. So they are slew dependent and load dependent, as well as they are state dependent. Since each arc is state dependent, the load model implicitly becomes state dependent. Pin level modeling is used in cases where the pin capacitance is independent of the output load. Now at lower geometries, the receiver pin capacitance becomes a significant portion of the total pin capacitance driven by the driver. And owing to the dynamic nature, since it varies, the capacitance varies as in different parts of the waveform, it becomes a complicated function of the receiver input waveform. Now, if your receiver pin capacitance is not accurate, then you're not able to compute a receiver model or receiver waveform. And if the receiver waveform is not accurate, then the accuracy of the downstream logic is impacted. So we need to have a very accurate receiver model to come up with an accurate receiver waveform for downstream propagation. Now, if you look at the CCS model, it models pin capacitance as a function of input slew. But to compute slew, you need to have some load. So there is an interdependency between slew and the receiver pin capacitance. So the solution to this is iterative. You start with some initial assumption, say the NLDM pin capacitance as the pin capacitance, compute the receiver slew based on that pin capacitance, then refine the capacitance based on its slew, and you repeat this process iteratively until you converge on the slew and capacitances or the desired level of accuracy has been achieved. Now, backmiller effect is another important consideration in the receiver modeling. So backmiller effect is basically comes into picture when you have a coupling between the receiver input and the receiver output of the first stage. So in this case, you have a coupling between the receiver input pin and the first stage output pin. And the transition at the two ends of this capacitance are in switching opposite directions. So what it means is that because of this coupling between the input and the output, the receiver will have, the victim will have to do more work to complete the transition. And because of this coupling, there are going to be bumps on the receiver input waveform. And these bumps, they typically occur on the tail. These are often hard to capture, and especially when you have got narrow slew thresholds like 30-70. For example, over here we have this input waveform, and this is the corresponding output wave, distorted waveform, which is having the impact of backmiller effect as well. Now, if we use a 30-70 slew, then we don't even reach the point where the backmiller started coming into picture. However, if we use a 20-80 slew, then we have covered a major portion of the impact of the backmiller. So a 20-80 slew would be more appropriate in such cases rather than using a 30-70 slew, which would be optimistic. So the next topic we have is multiple input switching. So current library characterization methodologies, they all consider a single input to switching. However, with multiple input switching together, the delay of a particular arc can become substantially less, which means that the library delays or the library parameters could be optimistic for an early delay analysis. For example, simultaneous falling transitions at NAND gate inputs will accelerate the rising output transition, and likewise, rising transitions at NOR gate inputs would accelerate the output fall delay. Now, to circumvent the impact of this multi-input switching or the optimism which is caused because of libraries not modeling multi-input switching, a designer has to resort to applying delays. And if these delays are applied globally, then they would cover for the optimism but probably cause undue pessimism in the system. And these guard banding approaches, which derate the entire system, can be very pessimistic for the entire design. So with Tempest timing sign-off solution, one can use the simultaneous switching inputs feature enabled to compute specific derating practices can be applied in specific cases, thus limiting the overall guard banding and reducing the overall pessimistic analysis. Now, SSI derate is computed based on the earliest arriving output arrival and additional transitions at other inputs. Transitions from other inputs should arrive in a switching window related to the first arrival. So let's see what does it mean. So for example, here we have a core input NAND gate, which has got similar inputs used, but the arrival times of the switching input is different. And corresponding to I1, I2, I3, I4, we have these 4 output transitions as well. Now, if you look at the earliest output transition, which is corresponding to I1, it is in this region. It starts from over here and it ends over here. And if you look at the arrival times of the responses corresponding to I2, I3, and I4, I2 and I3 responses are within this switching window of I1, but the response from I4 is outside the switching window, so I4 does not have an impact on the delay by the simultaneous switching from I1 to I arc. Now, the next step is in this process is to have I1 and I2 switch together. That would make things faster and reduce the switching window available for I3 to be contributing to the simultaneous switching technique. So with I3 switching, with I1 I2 switching, if I3 still lies in the switching zone, then another simulation needs to be done with I1 I2 and I3 switching together, or else you are done with it. Now, if you look at the airdrop analysis, so typically a voltage grid would have finite resistances, which would cause the voltage at the different nodes V1, V2, V3, and V4 to be smaller than the voltage supplied by the power grid. However, analysis typically assumes that these are ideal voltage sources, and this assumption can sometimes lead to failures which could be functional failures, timing failures, or clock signal jitter. Tempest timing solution, power integrity, provides unique integrated IRSTA analysis to solve and close these problems. Now, the methods used for airdrop-based analysis could be based on K-factor, or they could be multiple library approach. So with K-factor derating, we assume that delay is a linear function of supply voltage. And delay is computed at a nominal operating condition. And the airdrop is taken into account by doing a K-factor based derating. So the adjusted delay, which gets computed over here, is computed delay plus K-factor times the voltage drop. This would work for very small variations in the supply voltages. However, the most commonly used technique these days is to have a multiple library approach, wherein the designer provides multiple libraries at different voltages, and the analysis tool would then use those libraries to do a nonlinear interpolation between the libraries and compute the delay at the desired voltage at which the gate is operating. Now, air drop variations can also reduce the clock period available for accurate data capturing. Optimistic clock jitter can cause chip failures, while pessimistic clock jitter can cause overfixing and may increase time to market. Spice-based solutions can be highly runtime intensive, so there has to be some methodology which can be used to do this accurately. Tempest timing sign-off solution has unique capabilities to compute clock latencies for all endpoints using effective instance voltages for each of the cycles. With this, I come to an end to my presentation. Thank you for your time, and I'll be glad to take any questions you have if time permits. Thank you.
Okay, so no, let us take up some questions. Lalit Mohan Dani from IIT Roorkee has a question. Do the industry have methodology to extract design parameters, width, length, etc., for example, of a cell or delay path to optimize all these different variations? So what he means is that with parameters, do the for example, if for example, you have discussed the K factor delay variations, so considering supply changing and interpolating between different libraries and uh, changes with VDD, how one can estimate the changes in delay. Does the industry have a way of, suppose the library or suppose the threshold voltage changes by a certain sigma, or it change, or you on the fly you have a on the fly standard cell library development kind of, and can you estimate the changes in delays, etc., or library characterization with change in width or length or maybe the layout of the cell? Is there some such thing already there? That's what Lalit is asking.
No, at least there's nothing as of now which is available to do this kind of estimation.
Okay. So another question that Padmaja, Dr. Padmaja is asking is, what is effect of CPRR?
You mean common path pessimism removal?
Right, right.
Yeah, the impact of CPPR is mostly on the slack computation, because this impact of CPPR is taken to the slack computation itself. That it helps in reducing the pessimism of slack.
Okay. Another question from Sujesh from Analog Devices, I think, is timing window and sleeves. On that slide, question on that slide.
Yeah,
Does
okay.
STA tool have the timing windows and sleeves on that slide? Does STA tool have the capability to load an actual activity vector VCD and calculate timing window alignment?
Basically, STA tools would not use any of the activity-based solutions. It's more from static perspective, so we just do a worst-case analysis over there.
Right. So I have a question. As you mentioned, the transition is not monotonous in the sense that the transition can have bumps. That is being seen quite a lot in these days. So if the transition has in the last video that you uploaded, for example.
Yeah.
So if the transition has these kinds of bumps or discontinuities kind of in between, so how is that taken in the characterization input vector? If you take 30 to 70 transition as the input skew, then how do you take that bump into account? I didn't understand from the presentation. In Tempus, for example, now if you take 30 to 70 to be on the somewhat on the realistic side, so that if you take 20 to 80, as you were saying, that bump also is ignored. So that I agree. But if you take 30 to 70 transition, then how do you account for in the input table of the CCS data, say, or ECSM data? If you have the input table has only the sleeves, input sleeves, and suppose some effective output capacitance, etc., taken into consideration, then how do you take those discontinuities into account?
So basically, if you have a waveform available, then the library is used only for, say, the current lookup, or I'm not able to hear you.
Yeah, we are able to hear.
Okay, so if the library has got, so suppose we need the library, we're not using the delay or the slew tables per se for delay calculation if you have a CCS model available or a VO model available. Okay, but we need to access the data from the library, and for that we need an estimated slew. So if we use a 3070 slew which does not see the distorted waveform or does not see the impact of the distorted waveform, then the lookup from the library is not going to be very accurate. It's not going to be accurate even in the 2080, but at least it's going to be on the pessimistic side. And that ensures that we are not doing an optimistic analysis. The propagation of the bump is taken into account while doing the simulations. So when I say into account by simulation, is that when you're using the driver model and the receiver model to come up with the ordinary differential equation system, and then you solve that system using the currents from the library, at that point the bump of the input waveform gets taken into account.
Okay, so let us. There is no further question now, and let us thank Ratnakar Goyal for his timely and very important tutorial on. It was incidentally on timing, and it was a very timely kind of tutorial. So, and it was very important information, and thank you very much for the tutorial. It was well received.
Thank you. Thanks a lot for the time.
So now we have lunch break, and after the lunch break we will meet at 1:45. 1:15 Indian time, 1:15 Indian time, and so let's break for lunch. Thank you very much for the tutorial and for attending, for all the attendees for attending and the tutorial, and thank you.
You think that you lost, oh, I will take your hand and we'll rise up from the dust. Oh, here we go, 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 let us heal and grow. You won't be alone, we're unstoppable. Don't be afraid to show what we're going for. This is what we know. Here we come back to life, we're still breathing. Standing up, everybody's gonna see it. Oh, holding on. Even if we fall, we will rise up and we follow the path that we believe in. No, we're not gonna stop until we reach it. All you need to know is that we're holding on. We rise up from the dust and clear my throat. We rise up from the dust and clear my throat. We all have our reasons why we are on this track. Oh, we all have our burdens, yeah, but we just keep on fighting up, we never look back. Here we go, 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 let us heal and grow. You won't be alone, we're unstoppable. Don't be afraid to show what we're going for. This is what we know. Here we come, my tears, still breathing. Standing up, everybody's gonna see it. Oh, all you need to know is that we're holding on. Even if we fall, we will rise up and we follow the path that we believe in. No, we're not gonna stop until we reach it. Oh, all you need to know is that we're holding on. We rise up from the dust and clear my throat.
The future. How do you imagine it? Today, we're at the center of a tectonic shift in technology, where data, automation, and artificial intelligence inspire new forms of innovation and opportunities we can only imagine. Advancements in 5G communications, autonomous driving, cloud, and hyperscale computing are delivering a deluge of data, offering compute challenges for those most able to adapt. Strategic thinkers are embracing tomorrow's challenges today. The visionaries, the disruptors, the architects of possibility. They see that integration and intelligence will be designed into the products of the future. They know the industry demand for holistic system design, for mobility, hyperconnectivity, performance, and reliability. The path forward will not be easy. You will need a trusted partner who can help get you there. Someone with the breadth and depth of technology to anticipate what's ahead. A company with the right combination of tools and expertise to empower you to create the products of the future. Go on. Unleash your imagination.
Tu es trop grand pour comprendre des choses aussi petites.
Technology. It makes us think of numbers, data, analytics, and math. All the stuff that goes on in our head. But the truth is, the head is powerless when it's not fueled by the heart. And memory is the heart of technology, the driving force that pumps life into every product, application, and innovation it touches. Memory is the heart of science, allowing researchers to explore the microscopic detail of the human body and the infinite grandness of the universe. Memory is the heart of industry, making precision agriculture more productive, vehicles more autonomous, and smart homes more convenient. It is the heart of consumer experiences, making esports more active and VR more interactive. And it is the heart of AI, enabling it to do everything from make us coffee to make us laugh. At Micron, accelerating intelligence is more than a science. It's a passion, which is why we've assembled more than 37,000 thinkers and doers in over 18 countries who know that innovative memory solutions are essential to our future. A promise to continue pushing the limits, shaping the way we live, the way we work, the way we see the world. Memory is at the heart of what makes the impossible possible. And we are the memory makers. Micron, intelligence accelerated.
India is growing. In this changing India, design and manufacturing in semiconductors and electronics are important activities to boost its economy and meeting local consumption while being globally competent. Government of Karnataka, K-Tech and IESA together formed Semiconductor Fabless Accelerator Lab, a K-Tech Center of Excellence for Fabless, an initiative for developing and strengthening the fabless ecosystem in India. Suffle focuses on companies in semiconductor domain with their abilities to work on ICs and IPs. Suffle provides full access to expensive EDA and other tools and limited support towards MPW silicon tapeouts. Suffle also helps in mentoring, aggregated partner offerings, raising funds, aligning go-to-market strategies and various needs. Suffle initiative is much in line with the overall goal of Atmanirbhar Bharat. Potential in semiconductor industry is huge and Suffle helps explore the best of the possibilities. Located at MG Road, Suffle is easily accessible to all. Apply to Suffle program all round the year. Come, let's explore.
The speaker is Saurabh Tiwari. He is a principal engineer and technical manager at the Data Center Product Group in Intel. So he has completed his he did his masters in computer engineering from Indian Institute of Science, Bangalore, and has around about 20 years of experience in semiconductor industry. And he so Saurabh has some a patent from a US patent and has been technical committee chair for several conferences, and he has a Intel Achievement Award, which is one of the highest recognitions in his company, and he has contributed strongly to Intel's mainstream microprocessors for laptop computers and compute accelerator architectures for graphics, imaging, and artificial intelligence. So now let us welcome Saurabh for the tutorial.
By far, the greatest danger of artificial intelligence is people conclude too early that they understand it. Artificial intelligence is becoming a turning point in computing and is leading to paradigm shift in how we deal with data. Welcome to this tutorial session on artificial intelligence. My name is Saurabh. I'm PE in Data Platforms Group at Intel. I'm going to take you through some very exciting facts and details on what is happening in this domain. Let's start by looking at some of the cool AI stuff that happened in 2020. Here are the most interesting research papers of the year. In case you missed any of them, in short, it's basically a curated list of the latest breakthroughs in AI. You can now generate high quality face images from rough or even incomplete sketches with zero drawing skills using this new image to image conversion techniques. If your drawing skills are as bad as mine, you can even adjust how much eyes, mouth, and nose will affect the final image. This new model converts the code from a programming language to another without any supervision. It can take a Python function and translate it to a C++ function and vice versa without any prior examples. This algorithm represents body pose and shape as a parametric mesh, which can be reconstructed from a single image and can easily be reposed. Given an image of a person, they are able to create synthetic images of the person in different poses or with different clothing obtained from another input image. Let's look at some of the famous quotes from industry leaders. There is a growing belief across the industry that AI holds huge potential in almost each domain that we can think of. Do you recognize this image? So this is from 1997. Gary Kasparov playing chess against IBM supercomputer Deep Blue. It was a pair of 6-game chess matches between world chess champion Gary Kasparov and IBM supercomputer called Deep Blue. The first match was played in Philadelphia in 1996 and won by Kasparov. The second was played in New York City in 1997 and was won by Deep Blue. The 1997 match was the first defeat of a world chess champion by a computer under a tournament condition. Now let's look at this image. Do you recognize which one is this? This is from 2016, and here Lee Sedol is a professional Go player. He is one of the strongest players in the history of Go and is being defeated by a computer program. First, let me explain what Go is. Go originated in China about 3,000 years ago. Winning this board game requires multiple layers of strategic thinking. Two players, either using white or black stones, take turns placing their stones on the board. The goal is to surround and capture the opponent's stone or strategically create spaces of territory. Once all possible moves have been played, both the stones on the board and the empty points are tallied. The highest number wins. As simple as the rule may seem, Go is profoundly complex. There are an astonishing 10 to the power of 170 possible board configurations. Basically, it is bigger than the number of atoms in the known universe. This makes the game of Go extremely more complex and computationally intensive than chess. AlphaGo is the first computer program that defeats a professional human Go player. The first to defeat a Go world champion is arguably the strongest Go player in the history. By the way, this algorithm is based on convolutional neural networks and reinforcement learning. What is so significantly different about this event compared to winning the competition of chess? As I said, the board game of Go possibly has infinite amount of configuration or moves that one can make at each step. So it is not something that you can do mathematically or can solve on a supercomputer. It really requires the next level of intelligence or understanding or the feeling of strategy that only humans have so far. This is for the first time in history that you can see a computer program coming that close to human intelligence. And it holds a great promise of what AI can do in future for us. Now let's talk about a bit of history of AI. As you can see in this graph, there have been a lot of rise and fall on AI technology. You know, in general, hype is common in many emerging technologies. The AI winter was a result of one such hype. It's generally due to overinflated promises by developers, unnaturally high expectation from end users, and extensive promotion in the media. Despite the rise and fall of AI's reputation, it has continued to be developed into a new and successful technology. And finally, now I think what we see is a resurgence of AI in a consistent manner over past several years. Let's look some more. According to Gartner, deep learning has already crossed the innovation trigger stage. So what you see in this graph is different stages of innovation, and what we see on the peak of this graph, AI has or deep learning has basically reached the stake of peak of inflated expectation, where almost all of us are expecting a lot from AI. It'll be another few years before this technology goes mainstream. However, what we already start to see is many applications of deep learning that have made places in our lives. Let's look at some of the AI related publications and data related to that. If you just search in Google, you will find 370,000 publications that are related to machine learning or artificial intelligence. And here is a list sorted by the countries. You know, just to give you one more statistics, there is almost 50 papers published per day on the topic related to artificial intelligence today. The statistics presented here demonstrate exploding research interest in the domain of AI. Let's look at some of the computing trends, how compute power has increased and how data is increasing. What you see in this graph is a trend. First, let's look at the trend of compute. The computing power has increased 10,000 times since year 2000 in last 20 years. The cost of storing data has also gone down by around 3,000 times since year 2000. There have been an exponential growth in the data created, mainly due to rise of internet and the smartphone revolution and social media. Now we have huge amount of data available to us for analysis and for understanding. These three ingredients create a perfect storm for deep learning. The most important difference between deep learning and traditional machine learning is that this class of algorithm have their performance scale up as data increases. When the data is small, deep learning algorithms do not perform that well. This is because deep learning algorithms require a large amount of data to understand it perfectly. On the other hand, traditional machine learning algorithms with their handcrafted rules prevail in this category. Another good thing is that these algorithms are hungry for more and more compute performance, memory bandwidth, networking, connectivity, almost everything that we can also improve in hardware. Let's look at generally our distorted view of intelligence. We typically tend to think that there is a huge intelligence difference between humans, basically the difference in intelligence between the dumbest human being and one of the smartest human being. Let's take Einstein as an example. But the reality is that the intelligence difference between the dumbest and the smartest human is not that much. On the other hand, let's look at the graph of reality of intelligence. The difference in human intelligence compared to many of the animals is huge. And on this exponential curve of intelligence, what you see is where AI related intelligence lies currently. We are still far away from where human intelligence is. Let me start explaining some of the very basic building blocks for deep learning. And it is basically based on a block called neurons. And hence the whole algorithm as a whole is called as deep neural networks. And one of the entities of this neural network is neurons. While on one hand, in the picture you see on the left side, it seems to be inspired by biology. On the other hand, we can easily correlate the mathematical model of a neuron to a linear regression or a logistic regression, traditional machine learning algorithms. As you see, a neuron has a bunch of inputs, which we are calling, X in this case. Each input gets a weighing factor when it comes into the neuron, and those are called as weights, which is denoted by W. The mathematical equation of neuron or mathematical model of neuron is sigma of Wx plus B. B is a constant factor bias of a neuron. And typically before a neuron feeds its output, it applies a linear or a non-linear activation functions. And depending on the activation function, you can correlate neuron to either linear regression machine learning model or a logistic regression machine learning model. Now, deep neural networks are cornerstone algorithms that make deep learning happen. A neural net consists of lot of simple processing interconnected neurons. Neurons works on a simple to complex pattern recognition. They learn simple features in the first layers of the network. Some nodes are activated based on defined thresholds. These activated node inputs the subsequent layers of the network. In the following layers, it combines those features to derive another sophisticated set of features. The process goes on until it computes the final output in the output layer. Now, let's also talk a bit about what is an activation function that we saw here, which can make a neuron behave like a linear regression model or a logistic regression model. Activation function is a function that is added into artificial neural network in order to help the network learn complex patterns in data. Now, when comparing a neuron-based model that is in our brains, the activation functions is at the end of deciding what I need to fire to the next neuron. This is exactly what activation function does in artificial neural networks as well. It takes the output signal from the previous cell and converts it into some form that can be taken as an input to the next cell. We'll see later how we use this. Now, let's talk a bit about deep network. For me, studying logistic regression is a very good building block in terms of understanding machine learning, but it is also a very good building block in terms of understanding how neurons work and how first few layers of neural network work. Now, the first part on the left is trying to learn a good representation of data, and the second part on the right of a network performs a linear classification, or what we also call in machine learning terms as regression. Let's look closer at output layer. You see that it is a simple linear or logistic regression function. We have inputs, basically hidden layers, which have weights, where we do a dot product and that add a nonlinear function. A nice way to think about neural networks is it is generally split in two parts: the representation parts and the classification part. Representation or extracting the features is typically done by the first few layers of a neural network, and final, what we call as decision making or classification, is done by the last few layers of our neural network. It can be quite challenging to understand what a neural network is really doing. If one trains it well, it achieves high quality results, but it is challenging to understand how is it doing so. If the network fails, it is hard to understand what went wrong. While it is challenging to understand the behavior of deep neural network in general, it turns out to be much more easier to explore low dimensional deep neural networks, networks that only have a few neurons in each layer. In fact, we can create visualizations to completely understand the behavior and training of such networks. This perspective will allow us to gain deeper intuition about behavior of neural networks and observe a connection linking neural networks to an area of mathematics called topology. A number of interesting things follow from this, including fundamental lower bounds on the complexity of neural network capable of classifying certain data sets. What you see in these images is we have two classes in this data that I'm feeding to this neural network, and if I just do a linear partitioning of this data, I will not be able to classify in blue category or red category. But if I'm able to draw a curve which kind of goes as the third picture in this picture set shows you, then we are able to classify the data set into either blue or red category. What it means, and this is just another way of looking at the same data, is in some high dimensional space, there is a straight line separating the category of data that falls in blue category versus the red category. And our goal is to go to that high dimensional space where I can draw that straight line or can do a linear regression. And in this case, the line that is separating the data in high dimensional space is also called as hyperplane. Let's look at some more examples to get mechanics of neural network. Let's imagine we have two tags, red and blue, and our data has two features, x and y. We want a classifier that given a pair of xy coordinate outputs, if it is either red or blue, we plot our already labeled training data on a plane. A support vector machine takes those data points, outputs a hyperplane in this two-dimensional space. It's basically just a line, which we also call as linear regression model, that best separates the two tags. This line we also call as a decision boundary. Anything that falls on one side of it will be classified as blue. Anything that falls on the other side of it is classified as red. But what exactly is the best hyperplane? For our linear regression model, it is the one that maximizes the margin from both the tags. In other words, the hyperplane, again, remember, in this case, the hyperplane is just a line in case of 2D data, whose distance to the nearest element of each tag is the largest. So we are trying to look at the distance from blue and red tag. Now that example was easy, since that was clearly data was linearly separable. So we could draw a straight line to separate red and blue. Sadly, usually things are not that simple. Let's take a look at this case. It's pretty clear that it's not a linear decision boundary. It's not a single straight line that will separate both tags. However, the vectors are very clearly segregated, and it looks as though it should be easy to separate them. So here is what we'll do. We'll add a third dimension. So up until now, we have had two dimensions, x and y. We create a new z dimension, and we rule that it can be calculated a certain way that is convenient for us, which is z equal to x squared plus y squared. Now, if you notice in this case, it is an equation of a circle. This will give us a three-dimensional space. Taking a slice of that space, it looks like this. That's great. Now that since we are in 3 dimensions now, the hyperplane is a plane parallel to x-axis and at a certain z. Let's say z equal to 1. What is left mapping is back to the 2 dimension. So what we really do want to do is to map our hyperplane back into how it looks in two-dimension. And what you really see is it indeed is a circle in two-dimensional. So our decision boundary is a circumference of a radius 1, which separates both the tags. Uh, Next, we want to talk about the kernel trick. So let's start with saying what is a kernel. A kernel is a similarity function. It takes two inputs and spits out how similar they are. It basically utilizes two properties. Under some condition, every kernel function can be expressed as a dot product in the feature space. Now, we want to make sure that the kernel function is just a dot product of two vectors. And many machine learning algorithms can easily be represented in terms of dot products. So we knew that dot product of same dimension two vector gives us a single number. Now kernel utilizes this property to compute the dot product in a different space without even visiting that space. So imagine my problem is in 2D space as we saw in the previous slides. And what I want to do is to apply the function, apply the kernel in 3D space. For that, I don't actually have to convert the points back into 3D space and back again into 2D space. What I can do is I can have a kernel function that will convert the problem of a 3D space into 2D space in form of a simple matrix multiply operation or dot product operation. Now consider machine learning pipeline. You can take images, you can compute features, and you basically what you are trying to do is you are stringing features on each image into a vector. So you take an image, you take a filter, which is basically a another matrix, and you do a dot product of these two matrices. And if image contains the feature that is there in the filter, you will get a scalar output which is higher. Now, this is how the kernel method works. What I urge you to do is to read more about the kernel method, seeing how it is applying a beautiful trick of converting the problem of applying a function in higher dimensional space into lower dimension space by simply doing dot product operation, simply matrix multiply operation. Now, the next obvious question in front of us is, can AI get better than humans? Now, this is a quote from Stephen Hawking. Okay, let's look at this graph. This is a graph of development of artificial intelligence ability to play chess. The vertical axis is basically the results, and the horizontal axis shows the year or the age, right? Now, the red dotted line shows 2882 points. This is a result of human being playing the chess at their best. In the graph in 2006, a chess engine called Ripka, it overtook human capabilities by recording 2995 points. What we see here is in terms of game playing, we have gotten way too ahead, especially for example a game of chess, way too ahead using simple AI algorithms, better than humans. Let's look at two more very important problems. Now on the left side, let's first look at the left side. What it is showing, let me first give you the context. This is all coming from image classification problem, and ImageNet, which is a data set of over 15 million labeled high resolution images. It has about 22,000 categories. Now ImageNet competition uses a subset of ImageNet of around 1,000 images in each of the 1,000 categories. In all, there are roughly 1.2 million training images, 50,000 validation images, and 100,000 testing images. Now, what we see here is deep learning frameworks have managed to beat humans in image categorization or image classification problem back in 2015. So best of human capabilities in this data set is 5% error. What you see is 2015 onwards, we have AI algorithms that have an error rate less than humans, which means all our current image categorization or image classification algorithms have an ability which is better than humans on a data set like this, which is a pretty large data set. Let's look at the right side, where we see deep learning frameworks have managed to beat humans even in speech recognition. In January 2018, Microsoft and Alibaba demonstrated speech recognition models that were able to score much more than humans. The name of this challenge is called as SQUAD, the Stanford Question Answering Dataset. What you see also in the right side graph is before using DL, the incremental changes in speech recognition technologies were not much in last several years. The moment we started using deep learning, you see a huge ramp in ability of the algorithms to get not just better than humans, but consistently get better with time in a very short period of time. Now, what I want to draw your attention next is to look at some of the trends when it comes to neural networks for vision or image classification. We'll look deeper into three of these neural network topologies for image classification as they become very important part of object detection and computer vision pipelines. These are critical parts of many of the modern AI applications. So we'll start with AlexNet, we'll talk about VGG, and then we will end with ResNet. Let's start with AlexNet. Now, AlexNet is the first algorithm which utilizes deep learning technologies in image categorization or image classification problem all the way back in 2012. This was the very first time after a long time a convolution neural network based algorithm was used for image classification. And what we see is that this network had an accuracy of 84.7%. Compared to its second best in this category, which had an accuracy of 73.8%, a big jump in accuracy in a single year in this competition. This is an annual competition. And because of this, I would call invention or reinvention of using deep learning for image classification. One of the inventors of this algorithm, Jeff Hinton, is also called as father of deep learning. Let's talk about some of the properties of this network. The network consists of 5 conv layers, 3 fully connected layers. The activation function used is called as ReLU, rectified linear unit. The network has total of 62 million trainable variables, and it takes an input of 227 by 227 images, and its output is 1000 categories of objects which are found with a certain level of confidence. Now, the activation functions that this algorithm uses is either sigmoid or tanh. Now, there is a problem with this activation functions, and I won't go into details of this right now here, but you can look for it offline. The problem is that these both functions have a nature of saturation, and then they suffer from a problem while training this network with a problem called vanishing gradients. So this particular problem, all I can tell at at a high level is it makes the network very difficult to train. And all of the prior algorithms used sigmoid or tanh. AlexNet for first time used a simple ReLU activation function which does not suffer from a vanishing gradient problem. So it was much easier to train this network with limited compute compared to any of the previous convolution based neural networks. The next one that we'll talk about is VGGNet. Now, VGGNet was the first runner-up, and this is not a winner in ImageNet large-scale competition. It was a runner-up in 2014 in classification task. By the way, the winner was GoogleNet, which was the winner. But the reason I'm jumping into VGGNet is that in many of the modern image classification models, we use a lot of architectural concepts from VGG. Now, VGG16 has total of 138 million parameters. But the important point to note here is all the convolution kernels are of size of 3 by 3. So there is no different size kernel. Everywhere we use just 3 by 3 kernel. And in a moment, I'll explain you how 3 by 3 kernels are used for all kinds of convolution operations. Now, what is specifically different about VGGNet is all the variable sizes are used in the prior version, which we saw before, right? LXNet. We use 11 by 11, 5 by 5, 3 by 3 filters. Now, what we do in VGGNet is we use multiple of 3 by 3 kernels as building block and then replicate them to form a kernel of 5 by 5 or 11 by 11. So for a 5 by 5 conv layer, the number of variable is 25. On the other hand, two conv layers of the kernel size 3 by 3, which is how we are using it. If you see the animation on the right side, you see how a 3 by 3 kernel fills in, a matrix of 5 by 5 and then reduced to 1. So effectively having the same impact as a 5 by 5 kernel. So two layers of 3 by 3 can represent a conv layer of 5 by 5 in this way. For 5 by 5 single layer, you will have 25 variables, whereas two layers of 3 by 3, you will just have 18 variables. So it results in a reduction of 28% variables, which basically means the training will be faster. When you have less variables in a network, you can train the network faster. Now let's extend it. If I'm using a kernel of 7 by 7 or 11 by 11, in a very similar way, my number of trainable variables will reduce by 45% or 62% respectively for 7 by 7 and 11 by 11 kernels. So the main, let's say, advantage of VGGNet is a reduced number of trainable variables, which means much faster learning and much more robust to overfitting. Now let's talk about ResNet, which is, as I said before, is the first image classification network that almost, on par with or has beaten human abilities of image classification. Let's talk a bit about what is unique about ResNet. Now, first of all, neural networks are notorious. Sometimes they may not be able to find a simple mapping even when it exists. Say we have a fully connected multi-layer perceptron network and we want to train it on a data set where the input is equal to the output. The simplest solution to this problem is having all weights equaling 1 and all the biases 0 for all the hidden layers. But when such a network is trained using a backpropagation, a very complex mapping is learned where weights and biases will have a wide range of values. Now, what ResNet does is, ResNet architecture, it basically makes use of shortcut connections. And how does this shortcut connections help? They basically help in solving the vanishing gradient problem. So when you are doing the process of training, when you are propagating the error backwards in the network, the error will not only linearly propagate backward, but through these shortcut connections, a bigger chunk of error will also be propagated back into the network much faster, and hence the layer behind will see two impacts. One is the backward propagation through the network linearly. One is through these shortcut connections, and it will take both into account, and hence will converge faster. At the same time, will not see the problems of vanishing gradients. Now, in the table below, what you see is, I included Inception as an example as well. These four convolution-based neural networks are sorted with respect to their accuracy of finding, top 5 matching images in the ImageNet dataset, the number of training variables, and number of total floating point operations, because these are the good metrics to compare a vision-based network, right? Now, what you see here is this. AlexNet and ResNet 152. 152 stands for 152 layers of neural network. Both have around 60 million parameters. But, there is about 10% difference in their top 5 accuracy. ResNet is better by 10%, which is a huge leap in terms of accuracy for the same amount of parameter that you need to train. Training ResNet requires a lot more computation, but inference is much faster. So training ResNet, because it's a deeper network, it requires about 10 times more computation than AlexNet. It does require a lot more training time and energy, but the inference time is way faster. Now, VGGNet not only has higher number of parameters and total number of computation operations as ResNet, but also has lesser accuracy. So it takes more time to train a VGG net, but it also has lower accuracy compared to ResNet. So in both these parameters, ResNet is superior to VGG net. Training an LXNet takes about same time as training Inception, but memory requirements are 10 times less, with about 9% extra accuracy. So LXNet is superior compared to Inception in this respect. Now we saw image classification problem. Let's switch to the problem of language processing. NLP tasks vary in a broad range, and as the definition reveals, all of them are trying to deduce some meaning from our language and perform calculations based on language and its components. Now, algorithms that are based on NLP can be found in various applications and industries. Just to name a few, which you might encounter on day-to-day basis, is translators, social media monitoring, chatbots, spam filters, grammar checks, virtual assistants. What you see in case of language processing is that deep neural networks have managed to beat human in speech recognition. As I said, in 2018, Microsoft and Alibaba's speech recognition models were able to score much better than human on Squad Challenge, which is the question answering dataset system. Why the problem is complex and how is it different from the problem of recognizing patterns in images? So let's look at a sentence that you see on the left side, right? Each sentence has a bunch of words, and combination of words basically form clusters and context. When we speak or write in any language, there is this clusters of information, and it keeps flowing, and the context is sometimes very close within a sentence, or sometimes across the sentence. So that is why recognizing the context and understanding meaning, or even predicting the next word in a sentence is an extremely hard and sometimes often very sequential problem. Let's look at some of the other aspects of language processing. What you see on the animation on top left is how typically language processing is a sequential task, and it's not something that is massively parallel, unlike images or vision. Now the gates that learn data in sequence are important to basically keep or throw away the context, right? So what we use in language modeling is one of the entities that we use is called as LSTM. Now, what is LSTM? As you see, a normal convolution-based neural network does not carry a context. If you pass one piece of information, it doesn't remember when it comes to the next piece of information. So for dealing with language or speech, we typically have a neural network that carries a notion of memory inside the neuron, and that notion of memory is constructed using this framework called LSTM, or long short-term memory. Now I'm not going to explain LSTM in detail, but you can refer to LSTM later to see how they work. Basically, they provide gates when information is being passed through them, and the gates are basically to either remember or to forget. If a word is important, you want to remember it for some time. If the word is important but it has appeared way long back in a sentence or in a document, you may still want to remember because it may have a connection to a sentence much later in the book or in a chapter, right? Now this is similar to how we process text or language in our mind. When you read a review, for example, you see an example of a review here. When you read a review, your brain is subconsciously only remembering few important keywords. You pick up words like amazing and perfectly balanced breakfast. You don't care much about words like this, gave, all, should, all those connecting words. If a friend asks you next day what the review said, you probably wouldn't remember if word to word. you will remember the main points, like will definitely be buying again. If you are a lot like me, the other words will fade away from your memory, and this is how most of the language models work, right? They pay attention to some of the keywords and they will ignore all the connecting and other words. So that with that intuition, let's jump to what is the latest in the area of language. Google Brain and their collaborators have published an article introducing this new architecture. This is called as transformer. It is based only on attention mechanisms. Okay, it surpasses any other neuro-machine translation models that have been seen before, such as even Google's neural machine, which is used in Google Translate before, right? So transformers are apparently better than the previous models called GNMT or Google's Neuro Machine Translation. Transformer has been able to reach a new state of the art in translation. In addition to the major improvement in quality of translation, it also allows realization of many other natural language processing tasks. For example, it can be used for sentiment analysis, word prediction, analysis and finding of bad news and things like that. Now, this picture sort of just compares complex, what we call as recurrent neural networks, which I explained you, where you basically feed back the context as you see new words, and remember some of the words for things that are coming in future in a sentence. So those are the traditional sequence-based networks, or for NMT task. What transformer is essentially doing is it is able to establish connection both forward and backward, and one of the transformer based very famous model is called as BERT, which basically is able to see the connection between words in a forward sequence as well as the backward sequence. And generally the recurrent models are bad for parallel hardware, because their nature is inherently sequential. You got to process words in the order, whereas the way transformer architecture works, you basically are able to process words in sort of parallel and able to establish forward and backward connections between them later, and it allows for sort of batch processing of words when you're analyzing sentences or even multiple sentences, right? So it's extremely useful in terms of using the parallelism that we could see in image based neural networks, and this is why transformer is kind of state of the art when it comes to language translation. Now let me switch the context a bit, as we just got done with a brief journey of vision based neural networks and a little bit about language processing. Um, at a first glance, generally, looks like learning algorithm is most interesting and most important part of AI pipeline. Um, uh, I just want to place it in perspective and say the reality is that learning algorithms are very complicated and in most cases require a lot of time and effort to understand, but they are really a smart part of what we call as data science pipeline. Today the most important thing to learn is the whole pipeline, that is the process of gathering and processing data, pre-processing data, understanding the data, building the model, being able to evaluate the results, and then sort of fine tuning the model or data as needed. So what you see in this picture is what we call as crisp dm, basically a standard process for data mining. And believe me, when you want to take any AI algorithm from lab or demos into the real life deployment, each portion of this pipeline is extremely important, and not to be ignored. There is enough amount of let's say compute and algorithms that are needed to process data end to end as an entity, and one has to go through this pipeline many times to be able to refine the AI deployment pipeline in any of the business problems, right? Now, before I proceed further, let me quote one of the quotation. It basically alludes to the fact that while algorithms and how we model data and all these CNNs is extremely important, but to get these things deployed in real world, what will be required is a complete combination of hardware, software, and algorithms. And I think I can't agree more to this statement, as we will see in the next section of my presentation. We'll switch gears from the algorithm side of AI to more hardware and software side of AI. But before we get there, let me sort of refresh your memory from what I showed before. So let's look at the computing trends again. The picture on the left and the picture on right, both of which we saw before, but now let's look at it again. What it shows is there is a non-linear increase in data, but there is sort of linear and sort of plateauing out increase in the computing power. So all this computing power that has increased sort of linearly in last 20 years has allowed us to be able to process data up to this point. But as the rate of increase of data continues to be on a non-linear trend, and the rate of increase of compute is definitely not even staying pace with linear, I think there is a need for doing something different in hardware in terms of compute, and that is what we'll focus on. You also see on the picture on the right side, neural network algorithms with the current compute capacity, which is like our red line, are little better than our traditional algorithms, but if you give them more compute, they can take it. They can scale with more data, more compute. The beauty of neural networks is that the more compute you give them, the more data you give them, the better they will scale. It can keep going sort of in a linear sort of a fashion without plateauing out. And this is why the next part of this session, I'll be talking more about what we can do in compute in hardware. Now let's talk about why, if at all, we need a specific hardware for AI. So let's first start with what is a von Neumann bottleneck. Okay, so let me first give some history or background. We have come a long way. The first supercomputers or the first computers were very special purpose machines. It started like in 1822 with Charles Babbage, where he created a difference engine, which has the whole power of calculating polynomial functions. Now in 1958, Mark I, a physical incarnation of a single layer perceptron machine was created, and these was a kind of a combination of hardware and algorithm back then, back in 1960s. I think from beginning of these sort of algorithms, it has been understood that the unification of hardware and algorithm is needed for this domain. On the other hand, what von Neumann architecture says is a chip design consisting of a processing unit for computation, a memory unit for storing data, and a program containing instruction. So von Neumann architecture basically kind of separates the program from the computing unit, which you can take a program as a given entity and you can keep improving the hardware in terms of compute and memory. And this has worked well for general purpose compute, those which can be programmed for any desired task. So von Neumann architecture becomes a blueprint for current digital computer. It's probably not the best architecture for AI, right? And we are working with a lot of data, and data intensive programs, they require a lot of communication between memory and compute, back and forth, again and again. What it hints us is, if we go the von Neumann way, we'll basically be capped by neither by compute nor by memory, but maybe even the communication between compute and memory. So that becomes a huge challenge for AI programs. Even if I have a better compute architecture, I will not be able to utilize it simply because I'll require a lot of compute and memory to work together. Now, standard CPUs are definitely not much more efficient at these operations. As we saw, one of the very key operation that we came with the whole kernel method or kernel function is most of these transformations, most of the calculations that we are doing in these algorithms, we are kind of pruning it down to what we call as dot product operation or matrix multiply operation. And hence what seems like a good hardware for AI is something that can very efficiently multiply large matrices, because that's essentially what we are doing in all of these dot product operations in neural networks. So matrix multiplication and sort of lot of parallel processing, because each neuron is doing this matrix multiplication. So you probably need to do those many matrix multiplications in parallel for all the neurons in the layer and things like that. So all of these things are hinting at one particular thing, or at least two aspects that are required in the hardware. One is a lot of parallelism, because matrix multiply problem, as many of our hardware friends would know, is inherently a problem that can be made as a parallel problem. You can basically split the matrix multiply problem into a lot of parallel computation and then combination of results to find the output matrix. Now what we see as a historical trend is another machine which was not made for AI, sort of somehow fits AI very decently to begin with, at least, is GPUs. Why GPUs fit AI a little better than traditional CPUs is, as I said, we are looking at a problem that is inherently parallel in nature. We are looking at a problem of matrix multiplication, dot product, transformations, all the same problems that you will see in 3D graphics rendering. And hence, in terms of hardware, GPU seem to be a very close match to what you will look for in AI. And definitely, seems like it will be better than CPUs. Okay, so with this background, let's proceed a bit further. Now, there is a bit of dilemma when we come to the hardware. If we will design hardware, if we will design accelerators that will be optimized for the most frequent operation that I said, right? For example, matrix multiplication. But we'll not be able to do other operation very well, which maybe my CPU can do very well. It is possible that I'm too much hardening my hardware, and I'm sort of overfitting the problem to convolution problem. And as we see the trend in research, while a lot of AI in neural network processing or deep learning maps to convolution like problems or matrix multiplication like problems, not everything fits there, right? And coming up with newer and newer proposals for what kind of hardware suits AI very well. And what we need to sort of keep in mind behind the scenes is we need to ensure that the progression in algorithms, the progression in the workload keeps happening while we keep seeing more and more specialized hardware for the current day AI, right? So both of these are important. Now let's look at one click deeper into different kind of AI hardwares as they exist in the market. So of course the first and the most used platforms so far for AI have been GPUs, and why do they use GPUs a lot? Is because they support very high efficiency and high throughput matrix multiplication operations, and this problem by default is embarrassingly parallel problem. We can easily scale the algorithm. They don't need branching, and you can do away with fixed size memories and all those things. So this is why, as a baseline for convolution neural network kind of problem, GPUs are pretty decently suited and definitely better than the traditional CPUs. On the other hand, one can argue, and I can say, while I want to accelerate my workload, this is my killer app. I still want to keep the whole notion of programmability, and this is why you will see at least some of the organizations are investing in FPGAs as a hardware acceleration platform for AI. Simply saying, okay, I'll do the best design I can on my FPGA, and still have flexibility. Tomorrow, if the algorithm changes, if I, if I have to rewire the hardware and all those things, I'll be able to create a new hardware and burn it on my FPGA faster. So they sort of give me a sort of what I should say, efficiency versus programmability, kind of bridging the gap. Now, we will talk about what is the reality of the performance on FPGAs, though. Now, two more kinds of hardware that you will see in the market related to AI. The third one, which is not the very obvious one, because as we keep saying, CPUs, general purpose CPUs, are not that great at doing AI. What you see as a trend in the market, and some of the companies are leading that trend, is by having a very specific instruction set introduced in the CPUs, which is targeted towards AI application. So an instruction set that will do matrix multiplication very well, an instruction set that supports wider and vector operations in the CPUs. So the same good old general purpose CPU, but loaded with better AI capabilities along with a compiler and other things. So CPU is not like out of the race for AI. I think we see that CPUs have improved by up to 100x in some of the specific AI applications. Now the final, but definitely not the least ones, is custom ASIC. AI accelerator, we also call it, right? So these ASICs are application specific circuits. Now they are arguably much more efficient than traditional GPUs on both power, performance, the concentration of compute that you can put it. One of the examples is Google's tensor processing unit, TPU, and now you see the whole semiconductor industry flooded with tons and tons of such AI accelerator products. These are not so hardwired. They still can run most of AI algorithms with very high performance, and can supply same levels of power and performance with very low cost compared to GPUs. Some of the considerations for AI hardware. So let's first look at the main components that you will pay attention to in hardware. But let me start with some of the background here. In the human brain, memory and compute are not two separate components. They instead happen in the same place. I can't say this neuron is for memory and that neuron is for compute. We just don't have our brains wired this way. Memory just emerges from the way neurons are wired together, and computation emerges from the way neurons fire and propagate the information. So I think neural network sort of tries to represent both of these together. And while many of the current neural network processing tasks are done pretty well on the current hardware, it puts pressure on these specific components of hardware. The first thing is memory. What big neural networks require, and especially while training, is huge amount of memory. And as you saw, I spoke about 60 million parameters or 132 million parameters, each of them being a floating point number. So you can imagine that, and when we are training in batches, we require multiplied by the batch size kind of memory requirement for our network. So memory is one of the key consideration, and any amount of memory or memory bandwidth is not sufficient for neural networks. So it's one of the pressure points for the architecture. The other sort of pressure points is the storage capacity. The data set that we are going to use to train any of these networks contains millions and millions, and in some cases even billions of data sets, which basically requires a pretty good scalable and fast storage. The next thing is basically logic, which I would also call it as a compute. As we said, we do require some amount of matrix multiply type of compute, but on the other hand, maybe you do require a combination of a hardened compute that is doing matrix multiplication, but also a portion of compute that is more general purpose in nature, which can take care of the other nuances of algorithm, even non-linear functions like tanh, sigmoid, ReLU, all of those functions to be implemented somewhere in the hardware. And there are more such activation functions are coming. So it's required that the AI hardware compute is sort of little bit hardened for efficiency, but also a little bit softened for programmability, and it needs to be a good combination. Typically, it will end up being a heterogeneous hardware. Um, Networking is another component which people will think, why do I need networking for AI? Now, especially for training, the amount of data that you would be able to batch and train in parallel is huge, and typically even if we take the best of our TPUs or accelerators today, they will require to work in tandem with each other. Each of them training on different image and then sharing the weights or deltas later, which basically puts pressure on the networking subsystem of the chip or of the system. And while it is not obvious, I think networking is a very huge component in AI hardware considerations. Now let me kind of walk you through some of the key considerations of how AI hardware can take concessions and where it needs to be super efficient. What you will see typically is, especially for inference, low precision arithmetic is okay. 8-bit, 16-bit, many a times it is okay. Even for some limited cases of AI training, it is okay to be limited precision. It needs to have very high on-time memory and on-time off-time memory bandwidth, both in terms of capacity and bandwidth. It needs to have simple computations typically, so the control flow is not very important for AI hardware. Matrix hardware could be a building block for convolution, which is one of the very frequent operations in neural networks. You do require very high bandwidth connection between the chips, and I talked about the networking issue. You do need a sufficient amount of both compute parallelism and data parallelism, because you will see that in the applications. And training generally requires a large scale system, not one chip or not 10 chips, but maybe thousands of them together, right? So it's important that hardware takes that into account. Again, going over the architecture considerations a bit more in detail, what you see as a pattern, and this is not pattern of one or two of the companies, as you see how the semiconductor industry is progressing in this field. Computation, you will typically see matrix multiplication engine using either a technique of systolic array or a bunch of processing elements connected through some control and data movement kind of interconnect. You will see sometimes DSP cores being used, all kinds of scalar and vector processing units, memories, different kinds of memories, as many as are available. Everything can be used by these algorithms. There is a small increasing pattern of people trying to use in-memory compute or compute in memory, whatever you call it. You also see a pattern of people using content addressable memory, or CAM memories. Data handling, typically you will see the machine is able to handle low precision inherently, which is not the case with general purpose CPUs or not even with GPUs. It can handle sparsity, it can handle data transformations typically very easily. What are the value vectors of architecture, right? Different points of pull, I would call it. Low latency, if you are using this hardware in autonomous driving, for example, it will be performing some very critical functions which are time sensitive, so it needs to do inference in very low latency. So it's not important how accurate it is, but it is important how quickly you get to the decision. Low power, when you are especially doing inference on the edge. High throughput, you will be able to batch tons and tons of users in a single shot, especially in the case of cloud. Programmability, we need to support multiple frameworks, and I'll in a second talk about what is a framework. You need to have redundancy in case it is used in mission critical applications. Connectivity, networking, as I spoke, and security, so that the systems that we are designing are not easy to hack. What you see, and I'm not going to walk through the whole list in detail, but AI hardware ecosystem, it started mainly with Google, building a specific hardware for AI, which is called as TPU or tensor processing units. And again, I'm not going to walk through the whole list, but you see a bunch of companies, big and small startups, in many cases, are building very custom hardware for AI application. Sometimes very custom hardware for cloud applications, sometimes for edge or IoT applications. and this list is mostly out of date. Day by day you will see more and more companies jumping into building a specific AI hardware. Switching gears for a bit, from hardware to software, and I think software is a very important component of AI engineering. What you see is simple data from GitHub. And I'm not going to go into software details as much. You just see that, first of all, TensorFlow is most popular software framework for AI used by developers. And it has huge amount of investment when it comes to, if GitHub repositories are an indicator of how much software investment is being done in this area. You see tons and tons of them, much more than any other field of computational programming. I'll just walk quickly over the few key considerations for AI software architecture. You got to deal with heterogeneous parallel compute. You need to utilize them well. You will have to minimize the memory access and reduce the footprint, because if software is not able to reduce the footprint, we are going to land into the von Neumann architecture bottlenecks of compute versus memory. Utilize the memory hierarchy very well. If you have different hierarchy of memory, SRAM, DRAM, and any other secondary storage, um, trying to extract maximum parallelism. Generally, you will see a lot of very custom compilers in AI hardware domain, which are made to that hardware, and trying to extract most of the parallelism of the hardware. You do also need a lot of analysis tools to be able to tune the software to match the hardware very well. And what it requires as a middleware software is that it needs to be able to connect to most of the common software frameworks. And again, there are tons of software frameworks in case of AI. I'll just talk about one of them, right, which is most popular and most common, and many of the people agree to that. So ONNX, for example, is a software framework for data exchange for AI kind of topologies. It offers basically two main benefits. As a programmer or as a framework, all you need to do is to comply to ONNX. And from ONNX, as a hardware vendor, you basically will provide access to your hardware. So it basically sort of decouples the thing going on in AI software architecture world to hardware vendor side, and sort of allows this interoperability from building AI workload on CPU, GPU, and taking it to accelerator in a very, very seamless way without redoing the whole software. And this kind of framework or data exchange is extremely powerful and is needed in this industry right now. Simply because there is a huge amount of investment and innovation going on. A few arguments on why you see so many startups in AI, right? And first of all, I think this is one of the killer apps that people have been looking for a long time. And especially in the hardware space, there was hardware space never saw so much of venture interest in past so many years, right? It was all in software, services, those domains. It is for first time we are seeing very, very big interest from VCs in hardware startups. This is another reason of seeing so many AI related startups. There is a lot of possibility. Nobody has an answer, nobody has a solution, so there is a lot of possibilities that exist in being able to design a specific hardware and also specific software, very, very specific use cases, broad applicability. One of the I think um, uh, consideration is the investments are so big that even if you get a small portion of the pie, it is generally big enough. So that's why there are a lot of startup and small companies that are kind of rushing in this domain, and huge investments. And we all, I think, believe that AI is still in its infancy in terms of especially deployment. There is a lot of demos, there is a lot of work already done. But in terms of real life deployments, I think we are just beginning to see some of the applications of AI in our life. Again, I won't cover all of the spectrum in detail, but this is still very old picture, and you can see it crowded. If you kind of draw a picture of 2020 or 21, you'll see a picture that will not even fit in the slide. Almost everyone is sort of jumping on AI. Some of the common challenges in terms of AI deployment. I think there are a lot of last mile problems and execution problems. First problem, and I can sort of just summarize it. The very first problem is the problem of too much expectation. It's is people expect AI to work like a magic, which it is not. And we are still in our early stage of AI where we are able to apply AI to specific problem, to specific domains, and with specific amount of computations. I think it will improve, but for a real life deployment, we can't really bet our businesses on those things. So it is important to have realistic expectation and hence invest wisely into this. Moreover, I think in real life there is a lot of corner cases, a lot of things where it won't work. So a probability of 99% is probably not good enough in some domains. In many other domains, it may be fine, and this needs to be kind of a judgment call by the business in some sense, whether it makes sense to deploy or it is still time to wait for some more. So again, I won't go into details of each of these things, but so we saw lots of things that is happening in AI as we stand now. Uh, what I can say is there is a lot to be discovered, and this is why the picture of iceberg that you see on top left. But there is a lot more excitement in terms of lot of new and pushing the boundary kind of technologies that find their place when it comes to AI. It is pushing the envelope on hardware packaging side to be able to make bigger and bigger chips. I don't know if you saw the news of Cerebras system making a wafer scale chip for AI processing, or 3D chips, or whatnot, all kinds of silicon manufacturing and packaging technologies. There are research going on in terms of neuromorphic computer, completely different paradigm of implementing neurons. While all of those are early infancy, again just demos so far without any data, but they hold a lot of promise. People are looking at analog processing, to say can we mimic neurons with analog signals and not necessarily convert into digital, or even quantum computing, right? All of these hold promise so far, but as we know today, I think we are still, I'll give you a small data point that will uh, provoke this thought on how far we are from trying to mimic human brain, in terms of not just trying to mimic how we see pictures and all those, but in terms of efficiency. A human brain works on total power of something equivalent to 20-watt light bulb. That's the kind of energy efficiency it has. We are far away. We are nowhere close to human brain's capacity of intelligence, even on simple tasks, and definitely not close enough on power efficiency or energy efficiency of doing those tasks. So I think there is a lot to do, lot to go. It's very exciting. On the other hand, a lot of challenges in front of all of us, and I'm sure all of us can contribute in our own small and big ways in this domain. With that, it was my pleasure to present you sort of a big overview of this domain, what's going on and where do we stand. Hopefully it was useful. Thank you so much. Bye.
Thank you. Thank you, Saurabh, for the nice tutorial and overview. And so we have, I have one question. This, I mean, how do you compare between where is this different memories, memory options, compute in memory or CAM-based memories? Where do these fit in? I mean, compute in memory, I think fits in well for dot product MAC operation, isn't it? And how do they compare this CAM-based memories and compute in memory amongst themselves?
Right.
And
So I think each of them.
purely
Yeah, go ahead.
analog kind of solutions, like these are also compute in memory is also somewhat analog kind of solution, but purely there are some analog solutions which they using memristor, emulating memristors and these kind of solutions also people are proposing. Where do you see these?
Yeah, so let me start with the last thing first, which you said about memory stars or analog memories. Uh, First of all, I think all of those are in research still, not any practical product that at least I'm aware of, neither in the industry nor in any of the startups. So there is a lot of research going on that area because it seems quite promising in terms of density as well as how much compute near memory you can put. Um, from what I am aware of, and again, it's a limited knowledge of what is there in the public domain, is there are products that are having either compute in memory or compute near memory, but those are all digital technologies, as we know, right? So, and those are now I'll come to the first part of your question, which says, where do I use it in this whole neural network computation? The whole compute near memory or compute in memory is most useful in the cases where you do what we call as element-wise operations. So one bunch of operations are this whole convolution operations, which are sort of big matrix multiply sort of operations where you have accelerator. Now, other class of operation which is used, for example, in language models, BERT or transformers, is a bunch of what we call as element wise operation, where you have a bunch of data and for each element you want to do some operation before you write it. So you want to maybe add something, you want to subtract something, you want to saturate it. Each piece of data that you will be writing, you will do all these things. That is when it makes more sense to do either compute in memory or compute near memory, where you have to touch vast amount of data. You are going to be bound by bandwidth if you will do this touching of data from far away engine, which is not near the memory. So it's much more efficient, both in terms of energy and in terms of, let's say, computation efficiency. When the compute is much closer to memory, you have to do all these bandwidth bound operations on memory.
Fine. Thank you. Thank you very much for the tutorial. Thank you, Saurabh, for giving a big, a high-level overview also. So that was quite important. And thank you. We thank the participants. And so now we'll break for the, we'll have a short break and we'll start with the next tutorial within 10 minutes. So within 10 minutes, we'll start for the next tutorial. Okay. So we now give a break.
Thank you.
So the next tutorial begins at 3 p.m. Indian time.
It makes us think of numbers, data, analytics, and math. All the stuff that goes on in our head. But the truth is, the head is powerless when it's not fueled by the heart. And memory is the heart of technology, the driving force that pumps life into every product, application, and innovation it touches. Memory is the heart of science, allowing researchers to explore the microscopic detail of the human body and the infinite grandness of the universe. Memory is the heart of industry, making precision agriculture more productive, vehicles more autonomous, and smart homes more convenient. It is the heart of consumer experiences, making esports more active and VR more interactive. And it is the heart of AI, enabling it to do everything from make us coffee to make us laugh. At Micron, accelerating intelligence is more than a science. It's a passion, which is why we've assembled more than 37,000 thinkers and doers in over 18 countries who know that innovative memory solutions are essential to our future. A promise to continue pushing the limits, shaping the way we live, the way we work, the way we see the world. Memory is at the heart of what makes the impossible possible. And we are the memory makers. Micron, intelligence accelerated.
The future. How do you imagine it? Today, we're at the center of a tectonic shift in technology, where data, automation, and artificial intelligence inspire new forms of innovation and opportunities we can only imagine. Advancements in 5G communications, autonomous driving, cloud, and hyperscale computing are delivering a deluge of data, offering compute challenges for those most able to adapt. Strategic thinkers are embracing tomorrow's challenges today. The visionaries, the disruptors, the architects of possibility. They see that integration and intelligence will be designed into the products of the future. They know the industry demand for holistic system design, for mobility, hyperconnectivity, performance, and reliability. The path forward will not be easy. You will need a trusted partner who can help get you there. Someone with the breadth and depth of technology to anticipate what's ahead. A company with the right combination of tools and expertise to empower you to create the products of the future. Go on. Unleash your imagination.
India is growing. In this changing India, design and manufacturing in semiconductors and electronics are important activities to boost its economy and meeting local consumption while being globally competent. Government of Karnataka, K-Tech and IESA together formed Semiconductor Fabless Accelerator Lab, a K-Tech Center of Excellence for Fabless, an initiative for developing and strengthening the fabless ecosystem in India. Suffle focuses on companies in semiconductor domain with their abilities to work on ICs and IPs. Suffle provides full access to expensive EDA and other tools and limited support towards MPW silicon tapeouts. Suffle also helps in mentoring, aggregated partner offerings, raising funds, aligning go-to-market strategies and various needs. Suffle initiative is much in line with the overall goal of Atmanirbhar Bharat. Potential in semiconductor industry is huge and Suffle helps explore the best of the possibilities. Located at MG Road, Suffle is easily accessible to all. Apply to Suffle program all round the year. Come, let's explore.
now we start with our final tutorial. This is an invited tutorial. It is it is on low power design and predictive failure analysis in silicon in nanometer era. So I'll repeat: low power design and predictive failure analysis in silicon in nanometer era. So the speaker is Dr. Rajiv Joshi from T.J. Watson Research Center, IBM. So Dr. Joshi is a research staff member and key technical lead in T.J. Watson Research Center, IBM. He did his BTech from IIT Bombay and PhD from Columbia University. And he worked in a wide range of areas, right from microelectronics fabrication to memories and artificial intelligence, and he has about 250 US patents and 400 international patents, and he has about 200 publications. He has a lot of awards to his credit, and he is a governing board member of IEEE, and he is also an associate editor of IEEE TVLSI, and he has been on the program committees of several leading conferences, and he is an industrial liaison for universities as a part of Semiconductor Research Corporation. He is also in the industrial liaison committee of IEEE CAS Society. So now we will start to play the video. All the questions can be sent as usual in the chat box, and they would be sent as a to Dr. Joshi, keeping in view the odd timing or timing zone difference between his timing zone and our timing zone. He will take up all the questions over email and send a reply to all the queries. Huh? Yeah, so kindly also mention your mail ID when you put in a query. So that would be answered by Dr. Joshi within a short time, as it permits, within a few hours. Okay, fine. So let us start the tutorial.
Greetings from Rajiv Joshi. Today, I'm going to talk about low-power design and predictive failure analytics in silicon in nanometer era. The outline of my course follows with introduction, nanometer design challenges, planar versus non-planar devices, power issues, impact of technology, variation, reliability, Wieman variation, low power design techniques used for logic, memory, and alternate memories, and also giving you some predictive analytics, and finally summarizing the course. So what has happened in the literature that power dominance has taken place over the years? You can see that on the left-hand side, there is a power consumption, power wall, as a function of watts versus temperature, and bottom left is the power density versus number of years. And these charts are taken a little earlier in the game, where researchers predicted that if we don't fix power in processes, then there will be tremendous issues with the power density, and the temperatures can be as high as rocket nozzle. That was estimated around the 2007, 2006 range. And the rationale behind that was, if we keep on increasing frequency, that's what would happen. So on the right-hand side, you'll see a figure which talks about which shows the trend as a function of number of years, okay? And what has happened is the green line shows the transistor count, which has kept increasing. Now, these charts are up to 2010, but the trend has continued, this green trend, the transistor count has continued, and what has stopped is the frequency has leveled off completely because of these power issues. We cannot, increase the frequency infinitely. And many other factors have leveled off on that chart. So power is important and affects sub-nanometer nodes. Low power design technology techniques are necessary as transistor count increases. So what were the scaling trends before and now, right? So, of course, one of the knobs that has been played in the past was VDD, and also is being played today is VDD. And reducing VDD is a key solution for some applications. For performance, of course, it is difficult to reduce VDD. And for mobile applications or IoTs, I think it is very critical to reduce VDD because VDD directly affects, or square of VDD affects the power, dynamic power. So if you look at high performance device, what was predicted that the VDD would go down to 0.64, 0.62 in 2023, and low power operating power would require 0.6, 0.65, or around that, around that number. But if you look at, so these are ITRS charts in 2009, and the prediction was done for 2022, and then the voltages were hovering around these numbers. Now, if you look at recent IEEE International Roadmap for Device and Systems in 2020, it talks about the similar numbers, but in 2031 and 2034. You can see here. Why is that? Well, although it has been proposed that VDD is a key knob to play with, it is difficult to achieve lower VDD in operation. And industries have spent a lot of time on this in the literature. So let's keep thinking how we can reduce VDD, and this course will give you some idea about how to do that, and some of these techniques which may be feasible can be implemented in real product. So, impact of voltage scaling. Reducing the VDD results in energy efficient system. And if you look at the normalized y-axis versus the VDD on the x-axis, of course, lowering VDD gives you benefit in total power. As you can see, the power decreases, energy efficiency increases, which is on the right-hand side, right axis here. And when you start dropping the voltages, of course, when we approach the threshold voltages, the leakages start increasing, but still the total power will be lower. So that is one of the reasons why lowering VDD is a key factor in lowering power. So before doing anything with the circuits, we need to understand components of power, okay? Power dissipation. And power is broken down into dynamic power, leakage power, switching power, clock power, standby leakage, and active power, active leakage. And So total power is given by, say, some number, say half, because 50% duty cycle, frequency, C, capacitance, V, supply voltage, leakage times V, I overlap times voltage. And the total capacitance is the wire plus devices. So for high frequencies, dynamic power dominates. And also remember that as the number of transistors increases, the leakage power dominates. So these are the kind of things one has to remember. And whatever component we want to minimize in that total power equation, we need to go after those parameters. And you'll see that along this course. Another, another way of looking at it from leakage point of view is the I off is given by I gate, Giddle, and subthreshold summation, right? I gate and I Giddle increase as T aux lowers below 1.8 nanometer. I subthreshold strongly depends on Dibble, short channel effects, temperature, and floating body effects. And they can be captured in the equation that I off is equal to, some constant times all these parameters which are listed here, and you can optimize these through technology, circuits, and combination of technology circuits. Okay. And the leakage components, the mechanisms, are given in this nicely described in this chart. And all these leakages you can see, these are hot carrier gate oxide leakages, vertical you see, then subthreshold leakages, the PN junction leakages, all these components which are listed here, you can go through this and understand how they affect the device. And as I said, as the number of transistors increases, the leakage also will increase. Okay. Overlap current. Okay. In the circuit side now, if say the two pulses collide, meaning if in a situation, dynamic circuit, where overlap of active pulses, as you can see, with PFET on, NFET on, then there will be a direct path from VDD to ground. So insufficient internal timing margins and large slew rates result in these pulse collisions, we call it. Speed up in the internal paths, especially when migrated from one technology to another. And that is the important factor that one has to remember in designing dynamic circuits. And also in the static circuits, circuitry, there are slew rates, either too high or meaning too large. They can also cause the collision or a direct path between VDD to ground. So all these factors need to be considered to lower leakages. So near threshold voltage operation, this is a nice chart presented by Cowell in ISCC 2008. And again, emphasizing the fact that VDD is key to delivering solutions, particularly for mobile systems. Okay, so if you plot a maximum frequency, megahertz, and supply voltage, you can see that the power drops down significantly, as the voltage is reduced, and of course you get penalty on the frequency, right? That's obvious. Now, supply voltage versus energy efficiency versus supply voltage. And again, it improves significantly as the voltage drops. Energy efficiency defined as gigaops per watt, which is a very important number. And active leakage power also will decrease. So in order to improve energy efficiency, once again, it has been shown that, look, VDD is a key factor. Reducing VDD is a good solution for mobile systems. So let's look at some nanometer design challenges, planar versus non-planar devices, and the power implications of those. So technology challenges and the directions, planar bulk and SOI scaling limitations. So far, we have been playing in the past where planar, then came partially depleted SOI, and all these solutions afterwards came with some limitations, and bulk scaling issues, SOI scaling issues, and future for bulk and SOI double gate and the tri-gate as was defined by the industry. So if you look at the chart that I presented in a long time ago in 2013, and it was basically estimated or predicted that the gate per physical length is plotted on the y-axis and the years plotted on the x-axis. And you could see how the transition would take place. And you could see that from 0.13 micron all the way down to 22 nanometer, the technology node went from partially depleted to fully depleted with high K metal gate, and then the double gate, which we call it FinFET now. So this transition took place very nicely, and physical gate length reduced very nicely, and the performance, relative performance increased, as you can see on this axis. And so this is sort of the trend. So why was that? Because it was all about subthreshold slope. We want better subthreshold slope from the leakage point of view and lower drain capacitances. So from bulk and PDSOI, the fundamental limitations of silicon material characteristics prevail near the end of ITRS roadmap. Miniaturized channel lengths suffer from severe short channel effects, and back biasing is difficult with PDSOI because the box thickness or buried oxide thickness was much larger, and putting back bias is very difficult. So there came what is called as fully depleted, extremely thin body SOI, and the advantages were, as described by Olivier Fenot of Leti, that easier to integrate than the non-planar devices like FinFETs, undoped channel, reduced local variability, improved Vmin, improved electrostatic control, and controlling the active silicon thickness above the box or the buried oxide layer is key to VT control. And also, backgate biasing function of box thickness is promising. I-off current can be strongly reduced by the reverse body biasing or the reverse source biasing, and can reach outstanding values of 2 picoamp per micron. So these are the kind of findings, and fully depleted was also pushed for mobile applications by Leti and other folks who are working in that direction. So what are the challenges in the ETSOI? Well, ETSOI can be scaled to 8 nanometer node I mean, these are the predictions. If the box layer is scaled below 10 nanometer, the active silicon thickness can be maintained at 5 nanometer, and beyond that, nanowire technology will be employed. And these were predictions. And one challenge is the need to create multiple threshold voltages. The gate material work function is used to adjust the threshold voltage. And Letty describes its use of quarter gap metal, fluorine doping, and other methods to create the multiple VTs. Okay, and that is very important because you just cannot rely on the implantation. So these were sort of the prediction in early days. And as you know, that what has taken over is this FinFET all across the border. So let's talk about this 3D multi-gate transistor benefits. Okay, compared to planar transistors, its performance gain at low voltages, and you can see IBM also was working very hard at it for a long time, and Intel, came up with Tri-Gate, which is they are very similar in that they cover the gate. The gate covers on 3 sides of the of the source drain, and so it is a FIN. It is called as a FIN, one FIN, and it's a FinFET, and it has improved switching characteristics and higher drive current for a given size. So that's how the transition became. So the advantages of this gate performance was the dibble, as you can see, and the double gate also. So low dibble for double gate compared to single gate, and gain in drive current from improved channel control of double gates. So that is the electrostatic, which helps the transistors to gain more performance. And that was the advantage of using these FinFETs or multi-gate FET. Okay, so this is the advantage. So this is where you can see this was IBM work, and clearly shows the advantages in early days. This is again mu-gate performance, same FinFETs from Intel's perspective, and similar results. The IOFs were much better improved, 30% improved here as a function of IDSAT. And this is for NMOS, this is for PMOS. You can see, so superior short channel plus strain engineering leads to a strong performance with high K metal gate tri-gates, integrated tri-gate CMOS on bulk SI with high K metal gate, strained silicon, and dual epi. So those were the findings, and that these were the reasons why FinFET came into reality. So from the technology perspective, what can be done, I described to you. What is the present and the future? Current is the optical resolution enhancement techniques, high K metal gates, multi-gate transistors, fully depleted under-thin body technology, 3D wafer stacking, and beyond that, from beyond, this is the state of the art here, which is listed. And then you have a next innovation options, nano sheets, fork sheets. Okay, these are, gate all around the body. Then CFET, sequential JDs, dual Damascene structures, and then the replacement of materials here. Still copper will be used, but in the vias, there will be some refractory metals and things like that. So the trend will continue in innovation, definitely. And this will be the roadmap. This is recently published in the Semiconductor Digest. So it is really amazing how the technology has moved. Although the investment in the technology has increased, has quite a bit of investment-oriented nature to it, and requires money, cost, all those things. But researchers still keep on pushing the technology. And I think that is a very good sign that innovations has no boundaries. So what has happened for scaling on chip power, right? We scale. What is the idea behind scaling? First, we need to get the density. And the second thing is we need to have a low power. Why? Because if you reduce the dimensions, automatically you are reducing the coupling capacitances, all these parasitic capacitances around your devices. And then if you plot power as a function of frequency, normally this is what happens. If you have a node n as a function, node n, and this is the frequency on the x-axis and the power on the y-axis, and the node n will follow this trend. And node n plus 1, which is the further node, normally by 30% scaling, we are reducing the power, as I explained earlier, right here, by reducing. It drops down. If you continue to shrink by 70%, the power numbers go up. Power reduction goes up. Not power numbers, but reduction goes up. And from shrink to this, if you just shrink 30% and then use device enablement, okay, what does device enable mean? Meaning adding like new technologies like FinFET, nanosheet, or something like that. Then it would drop down further by 20 to 40%. So you need shrink plus the innovation. This is what happens. So benefits of scaling in recent nodes, 50% power reduction versus 70% what we used to get before, because we cannot scale 70%. Now the scaling has been reduced significantly. And that is the implication on power. Thus, technology, circuit, and system co-design is very crucial. Okay, so we looked at the technologies, how the technologies can help us in lowering power, leakage power, as well as active power. So let's look at the impact of technology, that is the variation, reliability, and VMIN. So nanometer challenges, those are variation in process parameters, right? So this is a inter and intra-die variations. Okay, this is a wafer, and you can see this is the full chip. So there is an inter-die and intra-die variation, could be Gaussian, could be different. And device 1 and device 2 in this, which are used in this chip, they could have a different channel length variations. There is a random dopant fluctuations. Okay, the dopants which are used for implantation to adjust VTs can vary a lot. And these days, the dopants are getting extremely reduced. So number of dopants, as you can see, can go down significantly, approaching. So the further nodes are not here, but if you just want to guess, those are well below 10 now, 10 atoms, dopant atoms. And then the frequency, variation you can see because of this could go up and down 30%, and as it is described here, delay and leakage spread. So the performance as well as the power will vary due to variation. So device parameters are no longer deterministic in this range. So variability aware design is very critical. What are the design concerns here? Power, performance, yield, and functionality. And variability concerns are global variation, random variation, reliability considerations, environment variation, all these things, and they outnumber our design concerns. So how to overcome this is a key challenge. Overestimating variability, over budgeting, operating at higher Vmin, hence power overhead. Underestimating variability can cause yield loss, performance loss, and extra silicon debug. So these are the main issues that one has to play with. So as I mentioned earlier, the dopant variations are very critical. And in that, there are random process variations. Simulated profiles are shown here. And you can see there are various forms of random dopant variations. Then there is line edge roughnesses here, polysilicon gate grain structure used in the gate or the metal gates, whatever you want to call it, and combined variability. So it varies. So it's a function of many factors for N channel as well as P channel. So N and P channel MOSFET under considerations are low power devices from ST Microelectronics, and all these data has been generated and published in this following in the note that I'm showing here. So variation is extremely important, and that need to be tackled, or we have to live with it. Then there is also long-term variation, or end of life we call it, kind of variation, and that is reliability and aging, right? So it's a negative bias temperature. We call it NBTI. If you apply negative bias to a PFET, its threshold voltage increases as a function of time. Okay, so that's the negative bias. It's called as NBTI, very popular. Channel hot carrier, which has these holes, can cause this kind of a failure mechanism. This is the gate, source, and drain. And there are hydrogen-oxygen bonds, and then all these bonds can be, some of these bonds can be broken after stress. Defects can be generated, and there will be a direct path between gate and to the channel. So it won't act as the device won't act as a NMOS or PMOS, but it will be like a resistor. And there is a time-dependent dielectric breakdown, so the current will just shoot up. All these things are very critical in analyzing or designing low-power circuits. So effect of manufacturing on the variation on Vmin. So manufacturing variability corners affect the design yield, that is NFET, PFET, as shown here in the 3D chart, where NFET is slow here, 3 sigma slow, where PFET is slow here, and the yield drops down, as you can see. So all these corners, conditions need to be taken care of. Vmin guard banding. That is, the additional Vmin guard banding is needed in face of increased variability. Inter-die chip variation, temperature, reliability, and other time-dependent variations are key. And Vmin as a function of time is plotted here, where it is ideal inter-die variation. If you include, then your Vmin will go up. Then inter-die variation added, then it will go up. So if you add these variations, the things will change. So this is where we need to guard band. This is how it is guard banded against the variation, the variability, and this is the guard band cartoon that you can see illustrates what exactly has been done in the VLSI domain. So in order to guard band these variability, we need smart solutions. The adaptive techniques and sensors address die-to-die concerns and need to react to environmental variation. For example, temperature can turn write delimited design to read delimited design. For example, if it is a write limited here, as it can be shown, by just increasing the temperature, the whole story changes, and you can see it is clean in the write area, but read area limited area for SRAMs or memories are very critical. So this is pertaining to memory solution here or memory observation. That is the impact of the environment, the PVT environment. So let's look at now the low power design techniques. The circuit for logic, circuit for memory, and non-planar SRAM. So technology, circuits, and system co-design can be well described using this cartoon. The technology guys focus on reduction in junction cap, control of substrate back bias voltages, process optimization, geometry and VT mobility, and circuit guys are worried about repeaters, buffers, trees, transistor size optimization, low voltage operation, dynamic control of supply voltage, gated clock, sleep mode control. And in system, you have selectively controlled logic and memory during operation, reduced memory access, instruction set optimization, low frequency, hardware accelerator, and all these factors. So these guys, folks, researchers working in this area, engineers working in this area, are thinking about different tasks to control. However, the final goal is still the same, that is lowering the power. Now, if there is a communication between all these three, the co-design between these three, then I think that is the really a great solution. So let's look at how the power reduction using capacitance reduction was done through the technology, circuits, and also system side. So frequency was, it is an example of L1, L2 caches, and you can see the VDD. The architecture guys or system guys will determine what voltages they want. Technology guys will come and say, well, we can push this to bulk. And then the innovators will come and say, well, we will have partially depleted SOI. And you can see that mapping the same structure, same topology, can reduce power if the technology gives you leverage. And that's what has happened. So the number of transistors almost remain the same in the last two columns. And you can see the power here, the power number, but the power number cannot be used directly because look at the frequency here and look at the frequency in the 130 nanometer SOI. So if you take those numbers and scale it with respect to frequency, for the same frequency, the capacitance increased by bulk over SOI is 12%. In SOI, you got higher performance with a slight increase in the in power, but if you scale it, you still get the advantage. Okay, so that is the idea behind this. So if you look at the variability impact on the on power and functionality, the process variability, which is the threshold voltage, length, W, that is the width, oxide thickness, is shown here. The leakage as a function of different combinations and permutations of these PVTs structures can be explained. So the leakage, subthreshold leakage goes down as you increase these parameters or the PVT variables. Overlap leakage, gate leakage, and the total leakage, and you can see how it drops down significantly. And the VTs do play a role. But remember that just by reducing or increasing the VTs of devices doesn't also go in the right direction, in the sense that the VTs, higher VTs will give you variations. So keep that in mind. So it's not a full blast solution, but it does help. So leakage control can be done in a variety of ways. Leakages in memories can also be suppressed by application-specific design techniques. Static multi-VT optimization, stack forcing, leakage tolerance designs. In dynamic, it's runtime based, adaptive body biasing, natural stack selection, sleep transistors, and there are many more which are coming up. A lot of these techniques you will find are used in the literature or used in the products already. So stacking is a commonly used technique, as you can see. The idea behind the stacking is to create negative gate to source biasing here, gate to source biasing for these transistors, and that way reduce the threshold voltage of the transistor. Once or increase the threshold voltage, I would say, of the transistor. The transistor threshold voltage will increase, so VBS will get negative, so threshold voltage will go up, so temporarily or dynamically, I would say, and as a result, stacking would help to reduce the leakages. Now, we know the 3 to 4 transistor stacks are maximum used because you don't want to degrade the performance also, because it's a combination of performance and the leakage, which is very important. So input vector selection by applying proper input vectors to circuits during the standby mode or operation, it is possible to reduce the static current considerably. This requires that the states of the flip-flops be saved, and several tools and methodologies are proposed in the literature to calculate the power that is utilized by these flip-flops or latches or the logic. And the example of this is the circuit chosen is a 3-input NAND, full adder and multiplier. And these are the SPICE simulations, and there is a genetic algorithm which is used and published in this paper by Professor Roy. And you can see that by doing these algorithms, genetic algorithms, you can apply these voltages, these vectors, not voltages, vectors, you can reduce the leakage power, and the delta between the SPICE as well as these algorithms is very small, and this is for minimum leakage as well as for maximum leakage. So in short, genetic algorithms give us guidelines, and actual implementation in SPICE also demonstrate the true results. Now, stacking for gate leakage as well is very important. It's shown by Professor Saibal Mukhopadhyay. And gate tunneling significant in thin oxide devices, input vector selection based on the relative contribution of the gate, and subthreshold leakage to the overall leakage. And it saves 44% savings in total leakage in 50 nanometer devices compared to the conventional stacking devices. Okay, and the gate current as a function of number of these vectors, the ratio of the devices which are used are listed here. But for the same ratio, you can see that some combinations, that is 1-0 combination here, really useful in reducing the gate current. Now, standby leakage reduction in the partially depleted SOI without body biasing, because body biasing is not available in PDSOI. So how do you reduce the leakages there? So if you have a circuit, dynamic circuit like this, then what happens is you have a low threshold voltage logic here. You can put that logic, and here you can put high voltage or high VT logic here. This is a low threshold voltage logic. So reducing the effective active mode are on a circuit, then increasing the standby mode are off without any body bias, induce modulation of V threshold, and you can apply a small capacitor to avoid the power bounce here, And that becomes very effective in lowering the bounce on this node, and thereby lowers the leakage because you are using here high threshold voltage device, then a small capacitor, low pass filter here to have the VDD bounce, and then those spikes could be reduced in the VDD and can get reduction in leakages. Another way of looking at it is called as a stacked wave pipeline using multi-VT schemes. And this is like a wave pipeline. So if you have a domino stage 1 here, then you can start by applying stacked high VTH PFETs, then stacked high VTH NFETs, so high VTH PFETs here, high VTH NFETs here, and this wave will continue in the next stage like this. So the output of a domino stage is high during the standby mode, and hence it can directly drive another domino stage with the appropriate standby signals. And it is very effective. It's like a skewed gates, but in a dynamic gates. And that will help to reduce the leakages. In a synthesis-based, multi-threshold CMOS based on path criticality, you have, as shown in this figure, you have nodes with low threshold voltages, nodes with high threshold voltages, and nodes on critical path listed here, okay, which are black in color here. So wherever there are leakages need to suppress, you can do that. While wherever there is a performance, you can put these low VT devices sprinkled around. These are the number of cases which are listed on the x-axis, and the standby leakage power is given on y-axis. And you can see that the two VTs with 1.0 VDD and with a 2 VTH can reduce the leakages significantly. So multi-VT adoption is very well known in the literature and can be used very effectively. But remember, each VT costs a mask and it is expensive. So power gating is a technique which is universally used. As you can see, the active here is your active device or active devices, and then you have a header device which is called as a sleep transistor, or footer device which is also called as NFET, which is a sleep transistor. And depending upon the utility of the circuit, you can turn this on off very effectively by turning on this transistor, and thereby you can cut power and reduce leakages very effectively. Now, sleep transistor and body bias for active leakage control. And this is shown very nicely. If you look at in this figure, what it has is the active logic. Then you have a transistor here, which is the header device, and the footer device. And the logic for that sleep transistor, which is called as a sleep transistor, which is a footer device, is different, and also the logic for the body biasing as well as controlling the header device is different. So that is the sort of area overhead that you have to pay for in order to reduce leakages. So when the microprocessor supply is collapsed, the reverse body bias is applied here. And clock gating reduces active power for idle clock, but does not reduce leakages. And the active leakage control with fast time constants for entering and exiting idle mode need leakage control techniques that not only result in significant leakage power savings, but also can be activated and deactivated quickly. So sleep transistor and body bias for active leakage control. It has low, you can see lowest leakage state is reached in less than 1 microseconds. Then there is an improvement of 37x in reduction, and these are number of permutation combinations, how you drive your PMOS transistors and body bias. Okay, the PMOS header and the body bias. So reactivation of block is achieved in less than 2 clock cycles. PMOS body bias reduces leakage power further by 2x with no performance penalty and similar reactivation time. So this, and in some cases you can get, if you have sleep body bias, forward body bias as well as reverse body bias, you can get 64x improvement in the leakages. Okay, and then you can go through this table and look at the area increase. It is less than 10%. So this is how you can reduce the leakages effectively. Now let's talk about dynamic leakage reduction. Dynamic leakage reduction, this is a classic example of a circuit which can give you even super low power and could be used for extremely low power application like mobile or IoTs and things like that. So power reduction through super cutoff feedback mechanism, and it is implemented in Cortex M0 processor. It is 300, close to 300 picowatt or 295 picowatt. It's published by Michigan Research Group by Dr. Lim. And you can see here the circuit involves an inverter here, which is cut off by NFET at the top and PFET at the bottom, just the reverse. So these two transistors are used, and using their VTs, it is possible to cut off in the standby mode the path between VDD and GND quite significantly. And that's what it is. So this sub-nanowatt M0 processor that was published earlier, which has batteries, the motivation was batteries suffer from limited endurance and scalability challenges, minimize active power for battery-less operation instead of maximizing energy per operation. Key requirement is to limit the maximum power draw, so the power is consumed as it is obtained, and reducing supply voltage further is ineffective, and dominant leakage power and robustness issues. It proposes a dynamic leakage suppression technique that consumes 10 femtowatt active power per gate. And this is the circuit which I described earlier. Two FETs, one is NFET and the PFET, are placed in the reverse fashion in an inverter stack. And this is the layout which goes with it. And the steady and dynamic state of DLS inverter, and these are the nodes, these are the timing diagrams or how the circuit performs, as you can see. And these are the voltages at the node that you can see. Because of these transistors, it is leveraging from their threshold voltages and cutting off and creating negative gate VGSs, and shutting off the transistor very effectively. So that's what it is all about. Dynamic power reduction can be also done through power-aware sizing, optimal routing, SoC with minimum wiring length, clock gating, noise suppression. And here is a system performance by using accelerators here. Okay? The performance is improved by 5x, and the system power is reduced by 1/5. And this is how it looks like, right? CPU and the number of accelerators, how they are doing in parallel, how they're shutting off, they're focusing. The accelerator purpose is to focus on one function. The program data memory here interface. So the dynamic frequency scaling, hardware accelerators is a very important here. So voltage scaling is very, very critical. Low swing signaling, SoC accelerators are very key. So these are the kind of things one needs to create dynamic power reduction. Clock gating. Clock gating is a well-known technique. Wherever the clock is needed, you should use it. And wherever it is not needed, it is gated. That particular logic or memory is gated. So it is very important from that side, and it's a well-known technique. Another technique is a power line boosting technique, which is very important in my opinion. And this is a memory application. We are talking about 6 transistor cell. So what happens is, in this situation, the word line is floating. Okay, and then there are 2 lines, power lines, which go, which are in the vicinity of this word line. And by switching these power lines, can cause coupling between the power line and the word line. And the word line voltage will go up. So it will boost the power of word line or level of word line, and that's what we need. So we want this pass gate of the memory cell to be efficient or stronger when we need it. So that's how the word line boosting is implemented, and you can make swapping, VT swapping, all kinds of things are listed here. And all these are efficiently included in the Power 8 analysis and also implemented on the chip itself. So it is excellent measure of how power can be reduced by implementing all these techniques. So resonant clocking, right? So it is very important it is basically recycling the energy through LC tank. And what you see here is an inductor. It is gated by a pass transistor, which is resonant enabler, and it has capacitors. And you can program it how much frequency you want by using LC combination. That is, square root of LC will determine the frequency will be, inversely proportional to that. And you can tailor that frequency with respect to your main clock. So the idea here is to use the LC tank and shut off your clock momentarily so that the energy will come through that to your circuit. So turn on your clock, charge this LC tank, then stop it when you don't need it, and then bring and use this LC tank to power up your this clock buffers and other circuitry. And this can be done on the fly without any issues. So clock power as a function of frequency is given here. And these are the results by implementing resonant clocking. So if you don't use any resonant clocking, as you can see, the power increases as a function of frequency, right? But if you use resonant clocking, and if your clock is in tune, if your resonant frequency is in tune with your clock at high frequency resonant, then you can get 37% saving here. See, 37% saving at 4 gigahertz and higher at higher frequencies. And if you want to do this at lower frequency, if you use another LC tank for lower frequency tuning, then you can still get significant amount of savings at higher frequencies. So you can see that dynamic power savings is really very impressive. Now I will talk about memories. So SRAM cell scaling, SRAM also in memories, power reduction is also very critical. And you can see that because the cell size as a function of L or the node, right? So it is dramatically decreasing. The cell size is going well below or well below 0.05 micron now. Okay, and these are the players here who are reducing the memory size. And key issues for both planar and non-planar SRAMs: low power VMIN, maintaining low VMIN in the midst of increased variability is critical. Cell functionality, read stability, writability, and timing of critical signals is very important. The array performance is also extremely important. So memories are crucial, and reducing VMIN, that is that VDD knob that I was trying to tell you before, has become very challenging for memories. So what are the low power memory design techniques? Well, leakage control mechanisms are shorter bit lines, bank selections, similar to logic, header footer devices, multi-VT devices, addition of extra transistors, on-demand boosting to improve yield and obtain low VMIN for conventional SRAM cells. Variety of techniques are proposed, such as dual static power supplies for SRAM, dynamic power supplies, dual supply, power supply boostings, techniques via interconnects. It is important to offer a simplified solution which improves stability, performance, and VMIN. So let's look at some of these techniques which are crucial in delivering this low power memories. So if you look at the low power and high performance memory design, our earlier work, you can see these are the number of banks in the memories. And here the usage of thin cell. Why it is thin cell? Because the number of cells on a bit line, the capacitance of that will be reduced because the vertical dimension of the cell is reduced. And then the capacitance will decrease, the performance will improve, the stability will improve. And all these techniques are listed in our IPs, publications, and all these things. So please take a look, and this will be useful in low power memory designs. So low power memory design in the memory, again, looking at the sleep bias techniques to reduce SRAM leakages. This is a 6 transistor cell. This is a true bit line. This is a complementary bit line. This is the power. And then it is tapped to a footer device, which are NFET and or PFET, whatever. And these are called as sleep transistors. And with applying slight bias to these transistors, you can lower the virtual ground voltage so that it would not leak further. That is the whole idea behind this. And you are cutting off from virtual ground to the ground using these transistors. And the actual implementation is given in these transistors. So take a look at these papers which are published in the literature, and you will see how these leakages can be, lower leakages can be achieved. So another one is what is called as high performance low VMIN circuit technique, where 8 transistor cell is used, and this is the first time we try to promote 8 transistor cell. And what happens is, even if 8 transistor is used by the leakages will be seen from bit line into the cell or cell into the bit line and may degrade its stability. So that is called as half select issue. To resolve that issue and show robustness of the 8 transistor cell, we implemented a gated circuitry with respect to gated write word line with respect to the read word line, so that 6 transistor port of the cell remains foolproof. Okay, so that the gated portion, the gated cells are bunched into one side and non-gated are on the other side. That is, the columns which are gating it they are not interleaved, but they are gated on one side. As a result, you will shut down the other cells, other column cells, which are not selected. That's how you would reduce half select issue. As a result of the chip that was fabricated, which is 4 megabit chip, and that chip showed VMIN, that is voltage the cell can operate at 0.4 volt. So in order to do the high performance, low power, using low power circuit techniques, we can also use global bitline restore circuitry using NFET by dropping the voltage of the global bitline, which is this global bitline. So automatically we get VDD minus VT. So there is a saving on the word line, on the global bitline. And So this is a smart way to select prediction to reduce the restore power, early and late word line gating features. Word line driver header devices also are used along with this. And output socket buffer concept, driver of size tune, load of each instance. So all these precautions or techniques are used to drive low power memories. Another technique which I have been mentioning was this technology knob, right? So circuit technology system co-design is extremely essential. And this was the early work where how the FinFET and the PDSOI compared when we took our designs from PDSOI to FinFET. So the active cell power as a function of VDD, and you can see the lower power by the FinFET. The FinFET demonstrates lower power because of the fully depleted body, lower C-gate, and lower IOPS. And thicker FinFETs, TOX causes dynamic power to scale slower with VDD for comparable operating frequencies. So another way of looking at it is what is called as adaptive word line underdrive for low voltages. So the word line, this is a paper from Kolar, and the word line drive is modified based on the feedback from sensors. So 130 millivolt reduction in Vmin was obtained, and so idea was to lower the operating voltage. And there are multiple ways of doing this, and this is one of the ways of doing it. And as a result of that, the voltage was reduced significantly. Now, looking at the memory technology power performance, the conventional memories are listed like SRAM, which is here, and other memories, emerging memories, which are listed. That is phase change memory, spin torque, MRAMs here, RERAMs, resistive RAMs, and all these other things are getting explored. Some of them are already in manufacturing, like MRAMs, and on a smaller scale, PCRAM, and RERAM is still getting explored. However, when we move from the memory to the non-volatile, meaning the volatile memory like SRAM to non-volatile, there are advantages as well as disadvantages. And you can see one of the advantages is the cell factors are very good. Power consumption is extremely good, and also the leakage powers and read-write powers are also extremely good. Now, the drawback, you can see some of them have these the number of read-writes, right? So SRAM is pretty good. PCRAM has issues, and other also memories have some issues. They are very limited compared to what SRAM can do. And their read time and the write times are also poor. So there are pros and cons of each technology, and the research in this area is continuing from the power perspective as well. So that's why I thought it would be highly essential to add these non-volatile memories from power perspective. That is lowering the power perspective. So technology and design innovations will continue. So far, it's like what has happened from year till today, in future. This is what is happening, and this is what will continue. And then the innovative part like nanosheets and other technologies will pan out in future. So that is what it looks like. But ultimately, the goal people are working towards is how to get the power, lower power, and get the density. These are the two key things which will be emphasized. And although, as I said, it is limited because of the issues, because of the scaling issues. So the low power summary, I would like to say that low power techniques and challenge are discussed for nanometer era in detail. Technology circuit system and co-design solutions for low power will be the mantra for fabrication. Conquering and predicting variability and reliability concerns are keys to achieving low Vmin. An accurate prediction of future circuit characteristics is required to enable assessment for all VLSI applications. Ultimately, cost-efficient techniques to achieve area, power, and performance functionality solutions will survive. Now, I will talk a little bit for 10 minutes about the predictive analytics, and then I will conclude. So predictive analytics in silicon, what is the problem statement? Smarter statistical yield methodologies, applications, and the summary. So the problem statements here is the accurate yield analysis and nanometer scale designs is very critical. Example of the problem is SRAM design yield. Regularity allows memory design to use the most aggressive design rules. But then there are manufacturing variations, as we have seen, right? And achieving high yield requires detailed analysis and accuracy in modeling of tails of variability distribution is very critical. So examining tails of distribution requires very large number of detailed simulations, and exploring tails of statistical variability distributions for accurate yield estimate is it's computationally and completely difficult, in my opinion, and very expensive and need fast algorithms. So what was done with that? So primary sources of variability is the variability in device parameters, that is PVT. VT variation leakage, variations, leakages can affect SRAM cell performance and stability. Floating body effect in partially depleted silicon on insulator and can have additional effects. And advanced device structures like FinFET would introduce variability. So there are alternate yield techniques called as Monte Carlo and its alternatives, right? Failures are largely independent, and achieving good yield on a large array requires very low cell probabilities. And if you take these circuits, like here, variables, VTN2 and VTN1, and you can see the failure region is very, very tiny, right? Meaning small. But what happens is if you use Monte Carlo, it spends so much time in the passing region, especially in that Gaussian passing region. And then it does not have enough time to spend on the failing region. So as a matter of fact, the whole time blows up, the whole computational time blows up. So it needs robust statistical methods to accurately estimate such a rate, to attack or achieve such rare fail probabilities. So there are some techniques like this. This is a sensitivity-based method where you have two variables on the y-axis. There is one variable on y-axis and another one on the x-axis. And you just use the sensitivity only in one direction. As a result of that, this sensitivity can cause problems, inaccuracies, okay, because it is overly pessimistic. Then there is a grid-based methodology. So grid-based is, you use the squares and only use the points on the squares to move in that direction for these two variables, VTN2 and VTN1. It gives you the failures, but again, it is a very slow process. It's extremely slow process because it has to go through every single node and look at the failure probability. So in order to do that, in order to get over these problems in the literature, we came up with what is called as smart statistical methodology. And this is the methodology that is used where this is the Gaussian curve that you see. Monte Carlo fails because Monte Carlo cannot go in the rare failure region quickly. And we want to go in this region, tail region, because we want 6 sigma or 7 sigma yield. To do that, what we came out with is what is called as mixture importance sampling. And this mixture importance sampling has, first we do it with uniform sampling. We use the VT variations using uniform sampling. Then we figure out the failure point, so a center of gravity of failure. So it could be in this region, say. This process, the uniform sampling, is very fast process. Once we are in this region, then we shift this Gaussian distribution of these each variable in this region. So we start sampling in this region so that we can go in this tail region very quickly. That is called as mixture importance sampling. And that is extremely fast, and I'll show you. So examples of speed up. So this is the Monte Carlo technique, which literally fails, and the speed up which is shown, log speed up, as a function of number of sigma. So it keeps on increasing with our method. As you increase the number of sigma, it goes high, much higher. And this table illustrates the advantages of this. One is the Monte Carlo samples, which is the 0, 1, 2, 3, 4, 5 sigmas. The mixture importance samples are listed in this column, and the speed up that you see are listed in this column. So we can get 6 orders of magnitude speed up using mixture importance sampling. And that is a phenomenal speed up that you can see and observe. So I think this is the technique that has been applied to many of these circuit topologies, and I will describe to you in this chart. The applications have been very wide, and the application domain for pervasive statistical methodology has been capturing process variability. It is used for random open fluctuation, which I mentioned, ion mismatches, end-of-life effects, particularly subject to bias temperature, instability, soft error rate effects, other random effects, accurate estimation of rare fail probabilities, random telegraphic noise, okay, and predictive capability of desired parameters, that is for circuit technology co-design. It is extremely important. Then other applications involve the design optimization and data reuse, optimal redundancy allocations, and statistical leakage analysis, modeling and impact, and the applications go on and on and on. So it has been really worked on very effectively. This technique has been commercialized from IBM side, and it is used by many companies now. And I would like to illustrate these, these examples are already illustrated here through these description on the left-hand side. And that's how you can get bigger bang for the buck using this kind of yield analysis. And by the way, the yield analysis is extremely important in memories because you want to target 6 sigmas and beyond. Otherwise, memory yield has no meaning because memories are not single or double or triple, but they are in terms of megabits, megabytes. So such techniques are extremely crucial. So I would, at this point, I'm going to jump very quickly on my slide about the reliability stuff. That is the application to the reliability. And what you see is the contours, okay, these uniform contours that you see of different colors in this chart. There are two power levels which are plotted. One is VCS, the other one is VDD. And this is a 45 nanometer hardware. And we are trying to do the corroboration of the technique, this mixture importance sampling technique that I described. And so this blue contour, what you see, is predicted using these two supply voltages for a circuit that is used, a chip that is used, memory chip that is used for this purpose. So blue means extremely high yield, very high yield, that is about 6 sigma, then slightly lower, and then this is the worst yield. So the dots that you see here on this chart, the dots, pink dots, blue dots, these are actual hardware. The chip was measured using these conditions, VCS this much, VDD this much. For example, for this dot, the VCS was this much and the VDD was this much. Okay? Using these dots, you can see that there was extremely great corroboration, because these dots which were selected here estimated correct sigma values, and the dots which are here which failed were also estimated by our mixes, that is mixture importance sampling technique, showed that indeed the chip failed here. So permutation combination of these values of VCS and VDD showed that there was great corroboration with the measured hardware chip, and the contours that you see predicted by mixture importance sampling matched extremely well. Hundreds of chips were measured here. Okay, so this is an excellent result with this technique. So the impact and the utility. This has been used for many years in IBM, and there are variations of this technique, as you can see in the literature. This technique was used in the Power 7, which was used in the smarter computing Watson system, which played Jeopardy again and won the Jeopardy. And it was a perfect example how a technique is developed, and it was utilized in the product and became really an important one, and also got commercialized. So this is all about predictive analytics. It is a short overview that I gave you on this topic. I mean, this itself is a 2-3 hour presentation, but I will conclude here with a summary that predictive analytics from the perspective of yield and parasitics of silicon is described. Accurate yield analysis with orders of magnitude of speed up. The variability analysis through multiple devices, device structures and device variables for both logic and memory. Excellent model to hardware corroboration. Successful deployed tool for the use of use in IBM servers and ASIC products, and methodology adopted by different design teams. So this was a really good story about this predictive analytics. With all this, I really appreciate your time and patience, and giving me the opportunity to present this course. Thank you very much. These are the selected references you can go through. Thank you.
Thank you, Professor Joshi, for your nice tutorial. I hope it will be very helpful to all the attendees in this tutorial. Since Professor Joshi won't be able to take these questions online in the live session. We will send your questions to Professor Joshi with your email ID, and then Professor Joshi will reply to your queries within a day or two. So we thank you all. Thanks a lot to all the attendees, Professor Joshi, and we will end the session today. So that finishes the tutorial part of the VLSI Design Conference. And we have tomorrow the opening ceremony at 8:30 a.m. India time. So I welcome you all to join the inaugural session, followed by some wonderful keynote and technical sessions. Thanks a lot, and bye for now from the desk of VLSI Design.